Okay, so this is day 2 of workshop 29 for winter 2023, the demultiplexing advice and best practices. And so where we ended up last time is that we were just basically starting our first example with a real run. And so this is ZBP 098 lane 1, which is a PE 5151 main reads, 8 nucleotide single index, the same as the lane physically ran. So there's not going to be extra cycles around in the raw run folder. And the submitter expects a 20 plex of libraries in here. And we'll start with the raw run folder as it will come off the instrument, as if you get it from a core. You can always ask the core if you don't. Raw run folders usually aren't our defaults, but we can provide them when asked. The cycle breakdown then would be 1 to 51 is the single N first main read, 52 to 59 would be the first index, and 60 to 110 would be the paired N second main read. And because this lane has been donated and kind of maintain confidentiality, since we don't care about the main reads, I've deleted all of the main read cycles data except for the first base of each of the 2 ends for the main reads. That also just makes things run faster and makes the file smaller and stuff like that. So it's just convenient, and we just don't need them for the purposes of what we're doing here. And I also deleted the sample sheet that used to be there, because you don't really need to know the identities of the samples either. So yeah, so I think we kind of looked at the on disk format a little bit, just browsing around. The major files being a couple metadata files. These 2 XML files are the most important. There is a blocks file that tells the converter the layout. Each instrument has different layouts for the wells on the tiles. And in the old days, the locations had to be called because they were grown randomly by kind of the raindrop process of bridge amplification. So there's this file that kind of declares the layout that this instrument's using for the wells. And then there's a bunch of filter files, which for every tile tells you which subset of wells in the full design are singly filled. And then, so it's the PF1 declaration basically. And then the main meat files are these CBCLs, which encode the ACGTN bases and the Q scores for them. And those are basically the yellow files are basically the files that BCL2FASTQ2 or BaseSpace or what any of the other converters need. This is the essential information. There's a couple other directories like interop, which contains some statistics that were calculated during the run. And there's a Illumina tool, SAV, that you can download. I think it's Windows only though. It's a GUI program that can visualize those. And that kind of gives you stuff similar to what you might see with like FastQC or FastP that you might be familiar with. It's a little closer connected to the actual image analysis and firmware and software on the instrument than those. It's kind of beyond our scope to get into those, but there can be interesting stuff in there, but that's a whole can of worms I don't want to get into. The other thing is that BCL2FASTQ2's default is to convert the entire flow cell. But often if you're getting like a run from us, you're going to only get a lanes data in there. It's a lane subsetted run folder. And so then you have to make sure you include the command line options, which I'll show here, that tell BCL2FASTQ2 to only convert 1 lane. Otherwise, it'll try to look for all the data and think the flow cell's the run folder is broken because it's missing files. The answer is that if you didn't, if it's not your lane is the other lane, that's why you don't get the data for it. Okay, so we're going to do this in Huffman, and unfortunately, the BCL2FASTQ2 resource requirements are pretty high. It likes a lot of RAM, like dozens of cores, ideally. The disk space needed will be multiples of the raw run folder size. The RAM, it gets really crazy if you have full grid unique duals. We'll get when we get to the paired N example. The dual indexing example later today. We'll talk more about that. But basically, this is basically the only real standard tool that you can run on your own. BaseSpace stuff is in the cloud. You don't really have any control of that inside. This is your tool basically. So for today's demos, I'll request what are modest resources for a BCL to FASTQ run. 3 CPU cores, 4 gig of RAM per core, 12 gig of RAM total. And for 4 hours, that'll cover our 3-hour presentation today. And I'm going to ask for them on Pellegrini purchase nodes because the Pellegrini lab has bought nodes in Hoffman, and I can get faster access to those, where if I go into the general campus pool, I may be waiting a while before I get those. If you are kind of a general campus pool person and you can't really get resources in any reasonable amount of time on Hoffman that is sufficient, I recommend you find some Linux machine somewhere that's of some size. It doesn't have to be a giant machine, but you know, these days 32 gig of RAM, 64 gig of RAM, nothing special. You should be able to find somewhere available to you some kind of large machine, moderately large machine to run BCL to FASTQ2 on. Okay, so here is, let's connect to Hoffman however you like. Okay, I'm on a login node. We shouldn't do computation on the login node. So here I'm going to get a session on an interactive Pellegrini node, 3 cores, 4 gig per core, 4 hours. And the high P is what says that I want it to come from the pool of nodes that my research group has contributed to. And hopefully I don't have to wait too long. Last few times I've tried in the last few days, it's been like, 30 seconds maybe, but of course the one time you want it to work, it'll be, it doesn't want to do it. Anytime. Well, while we're waiting, we can continue. Sure, I can see that. So in my scratch space, in the workshop, in the directory for this workshop, we've got all the files here. Now there's some extra files here because like I can't rely on this actually working live. So I do have some pre-computed copies. That's what these baked versions are. It's like a cooking show, right? You kind of do the prep of the one that you're going to demo, but then you can't wait for the oven to finish. You got to shoot the rest of the show right there. So you pull the already made one out of the oven. So these baked guys are kind of the pre-computed runs in case this interactive guy doesn't give us any love, basically. So this is the folder with the data for the raw, this is the raw run folder right here. This 2104 April 7th, 2021 on instrument A817, 239 scan on the instrument, this flow cell serial number. That's how the run folders are named. Here is the metadata files. And then inside the data directory, there's an intensities directory, there's the slogs file. In the base calls, there's the 2 lanes. We're looking at lane 1. There's the filter files to find the PF1s. These are the cycles that are left. All the other directories for the other cycles are gone. 52 to 59 is the index cycles. If you look inside any one of those, you'll see a single one of these CBCLs. This is an SP flow cell, only image 1 surface. Oh, there we go. We got it. And so you're just going to get one of these files. This bundles up information for all the tiles on. So like this particular file is all the information for cycle 52 of lane 1, all tiles on surface 2, which is the only surface on an SP flow cell. Okay, so it's got the ACGTs and Q scores in it in a binary format, which we know completely all the details of. If you really care to know, but you don't care. Okay. All right, so back to the top level of the workshop directory. A little small. And actually I that away because now we've got the real thing. Okay. So, okay, so I don't want to really get into, maybe in the advanced Unix course or something, we'll talk a little bit briefly about these process limits that the shell ulimit command can affect. But basically, these are lifting some resource requirements from whatever they're set to the whatever the Hoffman system allows us at maximum. So we're raising some soft limits to hard limits of 3 certain kinds. Don't worry about it. One of these things is like the limit on the total number of files that a single process can have open at one time. If you had a really big sample sheet to Demux, then you may BCL2FASTQ2 wants to write to all those files at the same time. So if that's thousands, you need to make sure that the process is allowed to have thousands of open files at the same time. So stuff like that. Okay, so BCL2FASTQ2, the most recent version is installed in the module system on Hoffman. This is the name. And so we can load that into our environment. And now we can run it and we see the command line help for BCL2FASTQ2. Okay, so it's available and work. You know, it's ready to do stuff, but we got to compose a command line to do what we want. So, like we talked about last time, the way that the bottom-up approach starts with is a non-Demux run. We just want all the index reads out of the thing, because then we're going to histogram the index reads, make some decisions, compose a sample sheet, then do the Demux run. So the first run of BCL2FASTQ2 we have to do is the non-Demux run. And so we will change into the right directory, because this is the compute node now, which we hadn't done that yet on. So we're in the right place now. And here is the command line we're going to run. Now, to get this started, because this takes about half an hour to run, I'm just going to copy and paste it in here and let it go so that it's working while we talk about the parameters in this command line. And you see here, it actually produced quite a bit of output right away. It's basically saying, you know, this is my version. These are the command line options you gave me. And then this is basically it just chewing through the command line options and just getting ready, checking things out, creating the empty FASTQ files for the results. And now it's going to sit with no output for a long time because it's busy now actually converting and writing output as it goes. And then half an hour later, we'll get some messages that say I'm done. If I use my other window and look, you'll see that we have a new directory that just showed up. So I'll sort by time. And so this directory is fresh. This is right now, this is the one that we're putting the output into. And if we look in there, we can see that we're getting 3 undetermined files. Because Demux is off, this is a non-Demux run, all the reads end up going in a single pile, which the default sample name is just undetermined, sample number 0. And so we get a set of files here. This is main read, which will be just a single base in our case because we deleted all the others. This is the parent end read, which is again a single base we don't care about for our purposes. And this will be the index read, which we very much care about right now. The I1 is the first index. And if we look here, those should be a little bigger, right? So now I've waited a few seconds and they're bigger. And so that's what it's doing. It's working. It's busy work. Okay, so what are these command line parameters? So the first one that's important for the non-Demux run is to say create FASTQ for index reads. The default is that BCL2FASTQ2 doesn't generate the I files at all, the I1, I2 files for index reads. Normally it omits them because it's assuming you're running Demux, and then kind of the index reads have done their job and they're gone and you don't need them anymore. And so the default is to not generate the I1, I2 files, but we need them. This is the whole point of doing this right now. So this command line option says, I want FASTQs for each index read. The sample sheet we'll just do from dev null. That's just an empty file essentially. So no sample sheet. That makes sure that Demux doesn't activate. You could just give an empty file here. That would be the same thing. This is just some like info. You know, you can do different levels of messages. Info is the last one before debug, so it's sort of the most verbose that makes any sense to run in routine versions. These are the parameters that tell it to ignore missing files, which are important if you have a lane subsetted run folder, because otherwise it likes to look, even if it's not going to need the other lanes, it needs to be reassured. It likes to look at them and touch the files and say, oh, it looks good. I'm happy. This just tells it, you know, if you're missing, especially, you know, if you're missing especially files in other lanes, just don't worry about it. This is a trade-off. Okay, we just talked about that. This is a trade-off between gzip compression level, so how much disk space the files have been crunched into versus the CPU time to compute them. 6 ends up being a good trade-off. It's the usual gzip scale of 1 to 9. 9 is the most, spend the most CPU time to try to get the smallest file, but the benefits really usually level off pretty fast. 6 ends up being a good trade-off. We in our session we asked for 3 CPU cores from the Hoffman job system, and so I will distribute those into 1 loading thread, 1 writing thread, and 1 processing thread. Ideally, you should have a couple more loading threads, a couple more writing threads, and dozens of processing threads. That'll give you a much better speed. 111 would work just fine. It's just going to be much slower because it's just using less CPU relative to wall clock time. So with three cores requested, we're just going to have it work with 3 threads. These don't matter because we aren't doing Demux and we aren't doing adapter trimming. So one of the sample sheets, I don't know if you've used like Illumina Experiment Manager to create sample sheets, or maybe you have a template in Excel you've been using or something. But Illumina sample sheets can actually have all kinds of parameters embedded in them, not just the data for that declares what the index reads are for which sample. And you can actually activate support inside BSCRC to, for example, do adapter trimming. I don't recommend that for a lot of reasons. One is that its adapter trimmer is pretty stupid. It's a pretty basic one. It tends to have false positive triggers. And it's often not the right adapter sequence, because maybe you copied a template that isn't appropriate for your libraries. Maybe your sample sheet got merged with other sample sheets by the core, and it doesn't really work. They may not have merged all the adapters right. I mean, it's just asking for trouble. There's much better tools that are specifically for adapter trimming that you run after the conversion is done, and that's what I recommend. They're much more flexible. Makes a lot more sense. And so I always just recommend disabling that, which essentially just means don't put the magic lines in the sample sheet that turn that stuff on. So things like the minimum trimmed read length and the mass short adapter reads, these are filters that say, like, if after adapter trimming the read got really short, throw it away, and so on. These just aren't going to, I throw them in here just to kind of talk about it, but these really don't matter because the way we're running this, the adapter trimming is off. It doesn't matter. Barcode mismatches is where in the Demux mode, you put the tolerance in. 0, 1, or 2 is the only thing allowed. We'll talk about that when we get to the Demux stage, but this is where you put in the 0, 1, or 2 Demux tolerance that it supports. This is where the option goes. But again, Demux is off right now. Doesn't matter what this is set to right. This is how you indicate that you only want it to convert lane 1. The S underscore historical, don't worry about it. The 1 means lane 1 only. The next parameter is one of the most important, this use basis mask. This is how you tell it how to compose the output files from the physical cycles that you have. The syntax for this can get really complicated and weird, but the subset of the syntax that I show you here is basically enough to do everything. And it's a lot easier to explain this subset than some of the weirder shortcuts that you can kind of do. This is the way I always specify is with this subset. So it's got little sections separated by commas. There should be as many sections as there were sort of major ends in the run. So if you did single end, if you did paired end sequencing with single index, that's 3 ends that have to be done, right? The 2 paired end, the 2 main ends, that's 2, plus the 1 index, that's 3. 4 is the most you can have because that's the 2 paired ends plus the 2 indices. If you did a single ended main reads and no indexing, it would just be 1. There wouldn't even be any commas. But so basically this first section to the first comma is for the first end that happened physically. Then this one is for the second end. This is one for the third end. So in our particular case, this is main end 1. This is index read, and this is main end 2, the paired end. The numbers are essentially act as repeated copies of the letter before them. So Y1 means 1Y. N50 means 50 ends. And you could really type out 50 ends, but at least we'll allow ourselves that savings. So that's what the numbers mean. And then, so what does the Y, Ns, and Is mean? So a Y means you keep the cycle and it composes a main read in the output files. It composes main read cycles for output. The N throws cycles away, okay? Either main cycles or index cycles. They won't show up in the output files. The I composes the index read output files, the I1 and I2 and so on. And if Demux is active, those are the cycles that the Demux decision is based on. Okay. So in our case, we want the entire index read to come out in a separate FASTQ file. And so when we get to the middle section, which is the index read, we want to keep all 8 cycles as index cycles. And so we say I8. The main reads, remember, I've thrown away the BCL data for bases 2 to 51. So we're going to have it just output, keep kind of the first base and then throw away the next 50 bases. So that way the output files will just have the single first base as their output. And that's all we've got data for anyway, right? But normally you would say, it's much more likely in a real run, you would say Y51, I8, Y51. Right? You want the entire lengths of the main reads, the entire index read, and so on. We haven't talked about UMIs yet, unique molecular identifiers, which are a way of dealing with both PCR duplicates and instrument-induced duplicates, like optical duplicates, XAMPP duplicates, and so on. UMIs are basically the index reads grow a little longer and they have randomized portions. We'll talk about that on day 3. At this stage, when we're doing the non-Demux run, we would keep those cycles as part of the output, probably. I mean, you could throw them away now too, but so if you had like an 8+8 base first index where the first 8 bases was the tag that indicates which sample, and the second 8 bases is the UMI, you would say I16 here and just have the output file have all 16 bases. Basically, we just want this non-Demux run to just show us all the data in the lane, right? We're not going to try to interpret it or move the reads around into piles. We just want the data out of the binary files that are in the raw run folder and into some plain text format we can actually do something with. Okay. The next few options actually kind of are the obvious stuff that has to be there. You have to tell it what the run folder directory is, the path to the run folder input. You have to tell it what output directory you want to write all the results into. And then it can also make more statistics for that SAV program we talked about briefly earlier. And this is the directory you want it to write those into. If you don't specify it, it'll actually stick them into the interop subdirectory of the input run folder. I don't like to do that because I like to think of this process as not modifying the input run folder, because you're going to run this thing multiple times and so on. So I'd like to keep the output just down inside the output directory anyway. If you're ever to really use these with SAV, you'd have to copy the files into the SAV interop place in the run folder, and then you could look at it together. But we don't care about the interop stuff, so no big deal. But that's why I put it down in the output directory, because that way all the outputs are kind of in one place instead of scattered in 2 places. Okay, and then the rest of it, this sort of I think it's here. This parentheses, these fancy shell redirects. This is just some bash magic that basically lets us record the standard output and standard error as the program runs into log files, while simultaneously letting the output scroll by on our terminal. Most of that trick is necessary is trying to keep the 2 separate. So we have both the standard output and standard error not intermixed. But here. So you see actually in my terminal, that's why I can see the output of the program. But if I actually look at my workshop directory here, let's look at the files by date. First, you see here I have a standard output log file and a standard error log file. Actually, so far it's written everything with standard error. But if I look at that log file, it's actually the same thing that I'm seeing live in the terminal there. So yeah, right here is the contents of this log file, and these are growing together. So that's just a trick you can use anytime you're running a command and want to both keep a log of its output and see the output at the same time. Okay, so yeah, so that we'll come back to this and when it gets to be half an hour and confirm that it's working. But again, I've got a pre-baked version I can take out of the oven and show you already kind of what's going to come out of that. So here is the non-Demux pre-baked output. This is the one we're generating right now live, and then this is the pre-baked output. Exactly the same thing I just ran it this morning, earlier this morning. So yeah, so here is what you get. These are the 3 main output files, but at the moment, the output file we really want to look at is the I1, the first index read. So let's look inside that. That is a FASTQ file like any other. Day 1, we went into pretty big detail about FASTQ files and what's the interpretation of every little bit of them. Let me reorganize that from 4 lines per read to 1 line per read. That's a little nicer to see. And there we are, right? So there's our index reads for, whatever this, here's the tile XY, and that's the index read for that one. And here's the quality scores for that. Now, most Demux pipelines, including all of Illumina's own, just completely ignore the Q scores for index reads, and we'll do the same thing. So we don't even really care about this column. We just care about this column. Okay. The other, like the read one, main read one, that's just going to be a single base. We talked about why. So there they are. There's the first base of these reads. There's some ends. Oh, if we go far enough, it should be something else. Here, I'll go. There's 100,000 lines in. Okay, so there's some A's, at least a G, and so on. So those are just normally those would be the full length of the main reads. There's some files in the stats directory and stuff. You don't care about those mostly. Same thing with the reports thing. You don't care about those. And the interrupt stuff has the index metrics out bin that SAV knows how to interpret, but you don't care about that either. So basically, the only file really we care about at the moment is this one. Okay. How are these things named? This is the sample name, which normally comes from the sample sheet. The Demux fail pile is always called undetermined. Since Demux is off, essentially everything ends up in the Demux fail pile. We didn't kind of give any piles for it to go to, so there's still always the default pile. That's what this one is. So that's where that name comes from. Then the samples are numbered 0, 1, 2, 3, 4, 5. Sample 0 is always Demux fail. And the sample 1, 2, 3, 4, 5 is just numbered in the order that they show up in the sample sheet. Then L001 means this is for lane 1. And we talked about the I1, I2, R1, R2, and so on. And then the 001 is a part number. So I don't even know if it supports this anymore, but you used to be able to say like, oh, put at most 5 million reads in a piece, and then it would break one of the output files if it was big into many pieces, part 001, part 002, and so on. I don't think it even does that anymore as an option. You're always going to just have part 1 of 001 here. That's what that 001 is from. If you did have to break files up into smaller pieces, for example, to run many hundreds of smaller jobs in Hoffman to get them all done faster, then you'd have to split it yourself and combine it yourself. That's something I'm going to talk about in the advanced Unix workshop next quarter. But okay, so that's the complete explanation for why the file names are composed as they are. And when we do the Demux run and have a fancier sample sheet, then you'll see all these parts vary in the expected way. Okay, so yeah, so the next thing to do is to make a histogram of these guys. Now you remember from day 1, like this view. Let me get a PDF from day 1. We had this kind of thing, towards the end. We had this view of index read space, right? So like this. Basically, this density plot that kind of we were imagining here essentially is just the histogram visualized. The histogram is just a textual representation of this space. So the centers here, we'd expect to be things very close to the top of the histogram by frequency, and so on. So basically, looking at the histogram is kind of looking at these kind of density plot pictures that we had as a mental visual model for kind of what the Demux process was about. So let's compose a histogram. Now, normally you might do a histogram. Maybe you would do something like read the whole file into R, and then you can histogram or whatever. You don't want to do that here because there's 500 million reads here. And in S4, there's billions of reads, right? You probably don't have the memory in R to suck up one of these whole files and keep it in memory all at once. Now, there's crazy things you can do in R that allow R to sort of deal with data on disk, and it sort of streams it as it needs it. It's very complicated. And it's just not necessary because the histogram is very easy to compose using just straight up Unix text utilities that are part of POSIX, and every machine has them. And they work quite well, very efficiently, and so on. And the output histogram is usually very small. And that is something we can load into R trivially. So this command line here is basically us making a histogram using just command line stock tools. So first we decompress the gzip file to get a stream of the uncompressed text. So the .gz, it's a gzip file, they are compressed. Gzip c-d will give us an uncompressed copy, leaving the on-disk copy alone. So, I'm not in the right place, is the problem. Or the file name is, yeah. So it's got the directory name in there. So let me back out to the top level, which is how the slide is phrased. So there we go. We've got the gzip. And gzip is now giving us the FASTQ file as plain text stream, leaving the on-disk copy alone. Then we pipe that to paste with 4 dashes, which another thing I'll explain in the advanced Unix. This basically turns it from takes groups of 4 lines, deletes the new line between those and replaces them with a tab. That's what's giving us the wide view, 1 line per read instead of 4 lines per read. So now we've got, you can't really see it, but there's a tab here, a single tab, a single tab, and a single tab. And then these are actually ordinary spaces right there. I think that's the only ordinary space in the file here. So three of the white space gaps are single tabs. This white space gap is a single space. So we have that. Then we cut out column 2, and cut by default defines columns by tabs. So this is going to give us the second tab separated column there. And what is that? Well, that's precisely the read, right? So now I've got just the reads, 1 to a line. Now we're getting somewhere. So obviously to make a histogram, we should sort that, right? Because if I sort it, then I take all the copies of a single guy that is scattered all over the file and bring them into just a block. Much easier to count the number of times it shows up when they're all in one place. So then we do a sort. And because this is a big file, sort by default tends to not use a lot of RAM. We're going to tell you can use 10 gigabytes of RAM. Sort for big sorts, sort will read whatever memory buffer size it's allowed to use. So it'll read the input in chunks, fill up its buffer, do the sort on that, and then write on disk the sorted version of that chunk. Then it'll grab the next chunk and so on. If your chunk size is big enough, you're not going to have that many chunks on disk to deal with. But now you have sorted chunks on disk, and those are way easier to merge into the sorted file than the random whole file was. Because how do you merge a whole bunch of sorted files? You look at the first line of all the pieces, and you see which one's the smallest. That's the first output line. Whatever file that came from, you go to the next line of there. And so you just have a finger that's got one place in each file, and you just kind of ooze down as you compare who's the next smallest guy to come out. And you can just in a single pass through all those files produce the sorted output file. That's called merge sort. Merge sort works very well for out of core large sorts where you have to use disk as sort of the main storage medium. But anyway, to make this go faster and use smaller pieces, and since we've got whatever 12 gigs of RAM we asked for, let's let sort use 10 gigs of RAM there. Okay, that'll help it do the sort in a small number of pieces. So let me show you that, but I don't want to make this fast when we talk about it. Now that sort's going to take all the time to do this histogram. It'll take about 5 minutes. But to make this faster, in terms of building this command line, right now we've got the cut F2. That's your reads there. Let's just take a small number of those, like maybe 1 million. So I'm going to take the first 1 million lines or so just to cut it down and make the rest of this exploration on the command line faster. And now this sort shouldn't take much time at all. So, and I'm not going to put the buffer size there because it's only 1 million now. Okay, so now, yeah, there's a few seconds, right? So we have only sorted the first 1 million reads now, but you're seeing what the data looks like as it flows through the pipeline now. And what do you see? Well, of course, the first reads that would show up would be whatever the poly A's are, because that's in dictionary order what would sort first. And I'm holding down it wasn't too bad. I was holding down spacebar, second screen, third screen. Oh, and now we see poly AT, right? And now I'm just going to hold down the spacebar, right? And so you can see now how. Oh, that's a big one, right? I'm holding down spacebar and the screen's going by, but the sequence isn't changing. So that's a high frequency guy. That's probably a real guy. Okay, but anyway, but we're making progress here. Now we essentially need to count the number of times each repeated line shows up. That is what the unique command does. Unique without any options would just give us a single copy of each line. The -C means put the number of times it was found on the front. So I now add the -C. And now you see we made a lot of progress. That's basically the histogram. Couple things that aren't so great. Unique -C uses spaces to pad this to the same, right, justify the number. And we don't really want that. I'd actually prefer the sequence to be first and the count to be second. And I would prefer it as a 2-column tab separated file and not half spaces. There's a tab here, you can't tell, but these are spaces and this is a tab. And let's just clean it up a little. So how are we going to clean it up? Well, you may have seen in Intro to Unix the awk command, which is just an easy way of simply doing very simple edits to text files on the fly, basically. And so basically awk runs this thing in braces. This is sort of an awk command in the braces. The braces don't have any qualification on them, so this brace thing here runs on every single input line. And what does it do when you get an input line? We print it back out. We print a string, a tab, and a string, and then a new line, essentially a 2-column tab separated thing. The first string is the second input column, and the second string we put out is the first input column. And awk with no parameters defines columns on the input by just white space. So it'll do exactly the right thing here. This is what awk will call the first column. It'll just ignore these leading spaces. It'll take the next non-white space blob, which is the number. And then this is a space that'll stop. This is now the first, this is $1 basically. And these will be $2. It's exactly what we want. And so we just do $2, $1 because I want the sequence first. That gets rid of the $1 doesn't have any of the spaces that are leading here anymore. So that just does everything we want. So now I will add that to our pipeline. Oh, there we go. And so now we've got a nice 2-column tab separated file, no weird spaces anywhere. The last thing that would be nice to do is that this isn't sorted by frequency, right? I would like this to be descending by second column because I want to see the most frequent guys on the top. So another sort. This doesn't have to be as big of a sort because this is the histogram, like this line replaces 30 lines that used to be there. I mean, if we go a little deeper, where's the big guy? Oh, 57,058 copies of this guy, right? So this is why the histogram is so much shorter, right? We just took all these repeated copies and shrunk them. So this one is going to be a smaller file. I'll just give it a gigagram for that one. And then the -K22RN means primary sort is by second column reverse numeric, which is exactly what we want. And then tiebreaker by dictionary order on the sequence, just to have it defined. And then we're really done. And so there you go. That's probably the most complicated shell pipeline you've ever seen, but hopefully you see just with very simple parts, we can build up actually quite complicated operation, which is histogram. Produce a histogram sorted by descending frequency. And this will scale to files of terabyte size if you have to. And this is no problem. It'll take a little while to run. As long as you got the disk space, it will finish. I took out the head 1 million there. So that was actually trying to do the real job. So where's the, it should go here. So head. Bang. So that is what we want. And while doing that explanation, I should have just run the whole command in the background so that it'd be done by now, but oh well. Okay, so I put it in the background. It's working. I think it takes about 5 minutes, but I have a pre-baked version of that one too, so we can look at the histogram before it's out. So now this is now the whole histogram. This is not a subset of the first million lines. This is on the whole lane. Okay, and what do you see? You can almost right away declare what the libraries, the expected tags are, right? All you got to do is look 30 million, right? You got to imagine the commas in here, right? So that's 32,120,011. 30, it's going down, but pretty slowly. Okay, then there's all of a sudden like a big break here, right? So like now we're down to 600,000. We lost some digits, right? There's a big break. These two guys, maybe we're not sure of yet. They're kind of in the middle. We'll kind of look into them, but kind of a first guess is that probably everything from here and below is base call corruptions of things higher up. And so probably your pool of candidates for what the canonical index sequences are for what's present is the stuff right here. The stuff right here to right here. That's the pool. So your question. But that maybe somebody remembers, that's phi-x. That's going to be phi-x. Phi-x doesn't prime in I1 these days. So it goes dark, and dark sequence is poly Gs. So, and that's actually going to be what the user missed in the sample sheet. They forgot we're going to check in phi-x, and the sample sheet's missing phi-x. So yeah, so we can look at, that's what we're doing. We're looking at the top. In this case, we didn't have to go very far before it's sort of like we hit this drop off, this real drop off that makes us think we're probably already seen what there is to see. So maybe it's these 20 in red, the first 20. or maybe it's these 22, which is with these two kind of transition zone guys, but the big representation drop at this point is kind of here. Here, how are we at here? This is like 600,000 and down, and these are like 30 millions. So what's that ratio? What is that, 50 to 1? So at this point, we're 50 times below the top guy. And at 1% base call error or something, we could have systematic corruptions around this level. So this is all consistent with sort of these guys. Now that's hand wave. We should do a better job than that. I'm going to show you a web tool in a second to do a better job than that. But this is sort of the logic we start going through. If this run was dual indexed, you'd have to do 3 histograms. You'd do the I1 independently, the I2 independently, and then you would concatenate the two I1, I2 together and do them as a pair. You can actually do even the concatenation all live. Again, advanced Unix, I think, is where I'll talk about some of these fancier pipeline tricks, where here we're actually running kind of a mini pipeline and then another mini pipeline. This is actually generating the I1 sequences, and this is generating the I2 sequences in line synchrony parallel. And then the paste will then put those two independent pipeline outputs into a single, just like we did with the paste dash, 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 dash. This is kind of like a 2-column paste where we're kind of taking the I1s will end up in the first column, and the I2s will end up in the second column. And so we basically now made a 2-column input file that just has the I1, I2 together here. And then we can do the same kind of sort tricks and whatever. We've got to make our thing a little longer because now there's 2, now it's like column 2, 3, then 1, because you're going to have 2 sequences there. We'll worry about it when we get to the dual index guy, but you can imagine how it goes anyway. So the other thing is that if you had UMIs around, you generally don't want to include the UMI bases in the histogram because the UMI bases are intentionally randomized. And that's just going to take all of your guys that are supposed to, where the tag is the same sequence, and scatter them all over the place because the UMIs will randomize it. So in terms of figuring out what's there and so on, you want to drop the UMIs. How you do that, you use another cut command in the middle, right? So remember this is spewing out the uncompressed copy of the FASTQ. This is going to a 1-line format. This is pulling out column 2, which is the second line in every block of 4, which is the sequence. At that point, we can then cut character 1 to 8. So that would keep the leading 8 characters of each index read, which would be appropriate, for example, if you had an 8+8 first index where the first 8 bases was the tag and the second 8 bases was the UMI. In other words, so just keep the first 8 bases, the actual tag. Then you can proceed with the rest of the histogram pipeline as was. Yeah, okay, so that's all good. We already talked about this blob, why you want to do this on the command line and not in R. You're not going to have enough memory. It would be slower anyway. I mean, it's just no point. This is pretty easy to do on the command line. Here is the user sample sheet that they gave to the core with the project names. The project names are over here. There's 2 projects inside this lane. Remember, this was supposed to be a 20-plex. So there's what is it, a 12-plex and an 8-plex. One project's a 12-plex, one project's an 8-plex. The names have been just anonymized here. They're just called basically proj 1 or proj 2, and then sample 1 to 12 or sample 1 to 8. Okay, but here are the sequences that the user is expecting. Okay. All right, so we'll put that to the side for a second. We'll come back to that once we've finished a little more in-depth looking into this side here. Okay, while we're here though, we can quickly check the PF1 rate. How well did XAMPP fill up the wells here of this guy? That's pretty easy to check because actually we can add up the number of the histogram just basically counted the PF1 wells by index read. Well, we can just, if we basically just added up this column in histogram, right? This column 2, if we just added up column 2, that's how many PF1 reads are in the lane. So all we got to do is another little awk script. This turns awk into a tab separated engine instead of just using any white space to define the boundaries. This is explicitly tabs separate the columns. The begin block only runs once when awk starts up, not every line. We set the number of PF1s to 0. Some of this you don't need to do because of the defaults in awk and so on. I'm being very kind of explicit here. It's easier to understand, I think, if it's all explicit rather than relying on a lot of implicit magic inside awk. This is the block that runs for every input line. If you don't like plus equals, that's the same thing as this. We add to PF1 the value in column 2, which is this. So we're basically just we're just adding up column 2. And then the end block runs once when awk is done. And so after we've seen all the input lines, we do a single printf where we print out PF1. The percent 17G could have been a D. I don't really want to get into it, but basically you don't know whether your awk is a 32-bit awk or a 64-bit awk, and S4 lanes can have more than a 32-bit integer's worth of reads in them. And so you kind of want to switch to floating point here because that at least gets you 52 bits, which is always enough for all the size of flow cells we have. Don't worry about it. Anyway, it basically just prints out PF1. And then we just feed it as input to histogram, right? So that won't take very long because the histogram isn't very big. Now the histogram goes on for a while. Okay, it's not. I'm just showing you the first here, but I'm going to hold down the space bar, and you can see it goes on for a while. It's not like, it's not just 20 lines. How many lines is it in fact? It's 25,697 lines. So we've seen almost 26,000 distinct sequences in the index reads, almost all of which will be at extremely low frequency. So so here I'm looking at the top of the file. I'm going to hit the greater than sign and less to go to the bottom of the file. Okay, and I'm now going to hit the B key to go backwards. So now we're looking from the bottom up. And what you see is that there's just a huge number of these guys that were just seen once, right? Eventually I'll get to the A's, and now we're seeing the guys that were seen twice. Okay, but here is why you have tens of thousands of unique guys, because they're almost all just seen once. Okay. Oh, our histogram, our real histogram run is done. I don't have to use the pre-baked one anymore. So we actually just generated this live one just now. I'll get rid of the word live on it now. Okay, so this is the one we regenerated just now. It should be exactly the same as the pre-baked one. We could actually compare them explicitly to say, are these really the same? CMP gave no output. They're literally the same bytes in the same order. It's exactly the same. Okay, so yeah, so let's run our little oct count up column 2. Bang. Okay, this is it. I'm going to put the commas in because it's hard to see what that is, but there, 496,216,179. That's how many PF1 spots are in this lane. There it is. And so then we can compute the PF1 rate because we know this is an SP flow cell. And from day 1 slides, we know that SP flow cells have exactly this many wells. And we just divide, multiply by 100, 78%. And this is the distribution of what's common, and that's right here. And so that's maybe on the low side of, not even that low. It's just kind of in the middle. It's fine. Nothing to worry about there. Some lanes fill more of the flow cell, others less, but that's just okay. That's just in the middle. All right, so here's the first web tool I want to show you, called Index Checker. Here is the link. In the slides, which you should have a copy of the slides from the email this morning. Everything that's in blue and underlined is generally a clickable link. So it should work. So here I'm going to go to Firefox and go there. Maybe I'll make this a little bigger. I can't go too big because I want to put some stuff on the screen. But this is a little, it's actually an R Shiny app I wrote, and it's very simple. You just give it a bunch of index mers, and then it just makes the little grid of comparing each of those to every one of those and tells you how many mismatches apart they are. Okay, so let's look at, say, we could look at, say, what did this user do, right? So the user, here's the user's sample sheet, right? So this is the design they came up with, right? So let me paste that into a temporary file. Here's a text edit on Mac. It's my usual text editor. That's just the user's sample sheet. And one of the tricks on Mac is actually if you hold down the Option key, you can actually do columnar selections. That's sort of a nice trick. So I just Option drag out a rectangular selection. I can then hit copy. I could paste that into a new window if I want. That's all it is that column. That's convenient. If you have a sufficiently fancy text editor, I don't know if Windows Notepad will do it, but all text editors that are kind of moderately sophisticated will have some equivalent to that. So let's look at the user's design. How close did the user's intended targets get to each other, right? So I can take that, copy it, go over here, paste it in. Okay. Analysis number 2. You may not have caught it, but analysis number 1 was the default list that's in this thing, just so it has something to show. Analysis number 2 is the analysis with the list I just pasted in. And what do we see? Well, it varies a bit, but the smallest number that's in this entire grid is 3. Okay, so the closest that the user has expected to mix the indices is they're all supposed to be at least 3 mismatches apart. That's useful for us to know because it kind of colors our interpretation of these guys, right? So if I see now one of these guys down here is 1 mismatch away from something up here, that's probably just an index corruption, right? But if I see somebody down here that's like 4 mismatches apart from everything, well, now I got to wonder if maybe there's something else in there that he, it's not on his list or something. Okay, so this index checker has a bunch of uses. One of the things you should use this for is pre-flighting your mixes, right? So remember on day 1, we were talking about minimum guideline, keep your intended lane, the entire lane mix, at least 3 mismatches apart, closest to closest. Well, here's your tool to check. Okay, you just got to gather your indices you're thinking about putting together, paste them in, and here's your grid. So like suppose I make a bad pair in here, right? So like these 2 guys, actually these are almost kind of like an indel apart, right? Number 1 and number 2. So actually the second grid it shows you is the indel version where you allow indels. And you see that number 1 to number 3 is a single indel apart. Now, for most kits, they're not designed to handle indels at all. So don't worry so much about this. We will kind of pay attention to indels a little bit when we interpret the histogram dynamically because indels do happen. But in terms of design, you're going to find it hard to avoid indels because the kits don't really give any, they were never designed with that even as a thinking. So this is one for pre-flooding mixes. You got to focus generally more on the mismatches only. And so if I were to sort of like, so it's a different mix, maybe somebody's thinking about mixing in another library in here. Well, so suppose somebody has one that's that one, right? And I just type that, and it's got, I just intentionally made that 2 mismatches away from this, right? So, and what do you see? Now you see number 1 and number 2 is 2 apart. So that's now something you probably don't want to do. Or they could be 1 apart, right? So yeah, so anyway, I think yellows are 3s and 4s, and I made 5s in gray, 5 and higher in gray, and 1s in red, and 2s are in orange or whatever. But, and then these numbers tell you the minimum value in each row. So you can, if you need to see the minimum in the whole matrix, it's a small matrix, it's easy, but you can just scan down this and you can usually pick out what's the smallest number in the matrix. Actually, it tells you here. It says the whole matrix range is 1 to 8. If I go back here to that, it's 2 mismatches. Right now it's 2 to 8. Okay. So hopefully you find that useful. Don't forget to include phi x, which in this case is the poly G. Is it 8 of them? There we go. So now we've got number 22 in here is phi x, actually no problem. It's actually 4 mismatches away from everything else. Often, however, phi x is not. Phi x is, there's a couple of standard kits where some of the sequences are extremely close to phi x. Just try, just avoid those. And where people get in trouble is that they forget that's there and they'll use that index, but now they got sort of like a phi x collision, which complicates things. Either you pretend it's not there and then it's either interacting with that guy or not, or you throw it in, but now your Demux tolerance is forced to exact mismatches only because you do have a conflict at 1 or 2 mismatches apart. Anyway, simplest thing to do is just pre-flight and make sure, just include it, and then you'll see the trouble before you actually attach a library to the bad, the conflicting sequence. The other guys you should always add generally is poly A. That occurs less often. So must have there we go, 8 of them. If you get the number, if these things vary in the number of bases, the thing your input does not meet all the requirements above. There's a blurb that says what their combinants are. They all have to be the same length. So poly A does show up less often than dark, but it does happen. And for phi x and index 2, there's a particular sequence you got to use. One of the day 1 slides had all the sequences for phi x. Anyway, just make sure those are in when you do your pre-flights. But hopefully this tool helps you do the pre-flights. The other web tool, which is the one we need to focus on more right now, is the empirical Demux helper, and this is the URL for that. This is another our shiny tool I threw together for this workshop. And this is more directly targeted at the problem of deciding what's in the lane. Okay, so the last point we had the histogram open was this. So we were thinking that, yeah, okay, these 22 guys are candidates for what we think is in the lane, and we think the boundaries here and things below this are not. So what you do is you copy the top of your histogram out, and maybe I should copy it out of the terminal because it's more like the situation. So, okay, there's it in the terminal. I gotta make my window a little smaller because well, maybe that's enough. I want to go past the boundary. You know, to see a boundary, you always want to see past it a bit. You don't want to stop right at the boundary. You want to see the boundary, both sides. So we'll go down here. Maybe we'll stop at 100,000. Where we'll go. I just copied that into my GUI clipboard, and in here you paste that in. Okay. The other number you need to have in here, you can leave it blank, but you'll get more accurate interpretation if you tell it how many PF1 wells are in the lane, which we just calculated, right? So we did that, that was on this slide. This is the number of PF1 wells in this lane. And so I'll paste that in there. Okay. So, yeah, so you're not gonna be able to, whatever, it's gonna scroll there, but it's also produced an analysis. And this is now to help you decide what's what. So it'll make a little more sense if I mark what we think is the situation first. So what you do is you put a little asterisk next to the guys you think are the real canonical targets. So for us, we actually think that all these guys that are like the 30 million ones and so on, these are all yes. We think these are all good. Okay. And we're not sure about these. Maybe I'll throw them in for now. And then we think these are not, right? At this point, we think these are. That's our draft one. Now let's look at the analysis down here. So the ones that are starred are in green, and the ones that aren't starred are in white. And the columns are giving you various data about those relative to the guys earlier in the list. So the first column is just the rank in the list, which this is from a histogram. It's going to be in decreasing by frequency. So that's frequency rank. This is just a copy of the sequence, the index read. This is how many times it's it's just repeating the data you put in right now. That's what these first columns are. It's just a repetition of what you put in. The next column is how big this is relative to the PF of the lane. So this is 6.5%. This single guy, the single index read is 6.5% of the lane. And so that's what this column is. Then this next column is the cumulative version of that. Right? So by the time I'm down here, like at number 22, he's only 0.7% of the lane, but cumulatively we've now seen 97.5% of the lane. And now you're thinking, yeah, we have seen most of it at this point. The next one is the cumulative, but it only counts the ones that are marked star. Now here it's kind of simple because I only have green and then white, but if we had green and white mixed together, then it would skip the white ones in the total. So this is the cumulative percent of the ones in green. Then these are the very interesting columns that help you judge things. So what these do is the first guy, there's nothing to do. But for each guy after the first guy, you compare him to all the green guys above him. And this is the closest those get in terms of mismatches, or with indels is the next group. So let's look down here. Well, so the first guy, of course, he has nobody to compare to, which is why it doesn't, it's not applicable here. So number 2, the only guy you can compare him to that's green is number 1. And he is 7 mismatches away from number 1. Number 3, you compare to 1 and 2. Those are both green above him. And it turns out he's 6 matches away from number 2. And because number 1 isn't listed here, number 1 has to be more than 6 matches away. Okay, well, so far those all sound very distinct. Down here, number 8, you compare to all of 1 to 7 because those are all green. He is closest to number 4, where he is 3 mismatches away. He is uniquely close to number 4. But that's, we kind of expect 3 mismatches in this design. So we're not too worried. In fact, we're kind of not worried at all until we kind of get down here. And now we say, oh, this guy, which was in the border zone, which we originally marked, he's only 1 mismatch to number 19. He's probably not a real guy that's independent. He is a base call corruption of number 19. In fact, a systematic base call corruption of number 19. So let's unmark him. Which one is he? He's the one just above poly G. So this guy loses his star. So now he's gone white. And that's because we don't think he's a real independent sample, empirically present. Okay, how about the poly G guy? Actually, the closest he gets to all the green stuff is 4 mismatches for number 16. It's probably real. I mean, it's 3 million. I mean, it's what, 4-fold down from the other bottom one here, you know, but so it's like, you know, way above this next one. And how about the guys where we think are below the boundary we were thinking of? 1 mismatch to 16, 1 mismatch to number 5, 1 mismatch to number 19, 1 mismatch to number 5, 2 mismatches to number 19. This is it. This is it. We're done. Okay. So, but the green guys that we've got marked now, those are the real empirical. Those are the empirical targets. That's what goes in the empirical sample sheet. Okay. So we have now determined empirically the set of indices that is kind of present in the lane. Now we're going to look at the user sample sheet and see how that matches up. Okay. So this is just going through what we were just doing. And we just talked about this. Yeah, so anyway, this one guy is kind of interesting because it's the first time I've shown you hard data, like evidence for that the systematic base pair error does occur. Because where's number 19? It's this guy. Number 19 is only 14 million. But here's a 1 mismatch error. You know, where is it, right? It's GT, it's right here, GTA, GTC, right? 6 million copies of this GTC. So if I put those two together, let's call that 20 million copies of this guy. But 6 million of them, and let's use very round numbers, so it's 5 million out of 20 is what, a quarter, you know? So basically something like a quarter, I think it's closer to 30% or something actually. Something like 30%, you know, I mean, there's probably more variance here, but as it turns out in this case, almost all of what's left for this guy is this one guy here. So the total for him is really going to be about 20 million. And so 30% of this guy systematically base 3 from A to C wrong in that pattern. It's not spread over all the bases or all the patterns. It's just this particular base in this particular way. And so that's an example of a systematic problem. Now, it's not a bad one here because it's only a single mismatch away. And the design is 3 mismatches apart. And it looks like when we're done here, all the green guys are at least 3 mismatches apart from each other. We're probably going to demux this thing with 1 mismatch tolerance. In fact, we're definitely going to demux this thing with 1 mismatch tolerance because otherwise you're going to lose this guy. Right? Otherwise, number 19's coverage is going to go down by 30%. So we're definitely going to. This is an example of sort of like why in this lane where 1 mismatch is sort of going to be necessary. It's actually going to turn out to be sufficient too. Basically, we don't quite know that yet. We'll have some R stats in a second to see that it's actually sufficient to do a good job too. But here's this guy alone says you want at least 1 mismatch tolerance. Okay. Okay, so you can read this when you have time. This just gives you, there's just various ways, there's like various indicators that kind of suggest whether one of these rows, should I put a star on it or not? Just sort of some things vote yes, some things vote no. There's just various indicators that kind of help you make that decision. We actually talked about a bunch of those on day 1, really. But the next step, now that we've decided, we have now decided that there are 21 empirical targets in this lane. Now we look at the user sample sheet. How do they match up? The user only expects 20. So how is it? Now you can have all kinds of things here. You can have extras on this side, extras on this side. You know, so basically there can be extras, missings, you know, and maybe the sequences here don't quite match the sequences here. Well, this case is not too bad at all. In fact, it's a perfect 1-to-1 matchup with just a single extra guy. Okay, that poly G is extra. Here the lines show you the pairing. These are just sorted by sample name, really 1 to 12. These are sorted by frequency, which and actually you can already kind of see that like whatever project 2 is has a higher frequency, tends to have a higher frequency than project 1. That's very common. Is that, you know, each project has been prepped by one person or something. When you mix them, kind of, you know, each individually, they're all sort of in little varying zones, but when you mix them together, like these will be over here and these will be over here, and the variation may not cross. So kind of like, that's why you kind of see like this visual parallel lines here. It's because all the high guys end up being from project 2 here. That's very common. Okay. Yeah, some of these larger paragraphs you can kind of read when you have time, because if I say everything, we're going to run out of time. We need our list of 21 guys because R is going to need those. So before I forget, we're going to put those in a file. So I lost. We're going to lose our Demux run because we let the terminal sit idle too long and we got disconnected. Yeah, oh well. That's okay. We have the baked version of it, so we're still going to do what we need to do live. I mean, presentation wise. Okay, so in this file, we're going to just put the list of the 21 guys that we determined are here, and I think it's this file right here. So there it is. Use whatever text editor or do it on your local machine, copy to hop, whatever. I mean, just make a file with those 21 entries in it. Okay, that's this file. And oh yeah, right. So in general, this process is quite complicated. I mean, because on when things go well, it's just a perfect matchup and there's nothing to do. But then there's sort of mismatch, differences between the two sides come in degrees. They can be very close or they can be very far apart. And just sort of, you got to sort of work at trying to figure out what happened there. Here, not too big, not hard to interpret at all. Just what's the interpretation of this guy? Oh, but then you should think poly G, dark, phi x I1, probably phi x. And the user sample sheet just forgot to include phi x, which almost all user sample sheets forget to include phi x. Now you know. But this is clearly to make it a slam dunk, you would have to do the Demux and then look at the reads in this pile, and you would check them against the phi x genome. You could do a little alignment to the phi x reference genome. That would finish the discussion as to this being phi x not, because you can get dark poly G from other things too. But 9 times out of 10, this is going to end up being phi x. And what happened here is that the core spiked in phi x and probably spiked it in at about 1% in the end. When we convert all these final counts to percents, that'll be like 0.8% or something, which is right in line with where the 1% should be. Well, we know that this lane in total has however many reads, right? Whatever it was, we figured it out. 500 million. So 1% would be 5 million, and a little less than 1% would be like 3 million or something, So anyway, so where are we at with this guy? 3 million, So it's right about kind of, you already can kind of tell it's in the right vicinity to be phi x. Oh, here's the 5 sequences again. Poly G I1 currently sequences I2 as this. Older chemistries on NovaSeq sequence I2 as this. There's the sequences if you need them to paste into index checker or add your sample sheet. Oh yeah, we could actually start composing a new sample sheet. Yeah, we really need to do the R analysis that's coming up immediately first. But at this point, you could kind of start composing your new sample sheet. Sample sheets can be very, very simple, plain text files, comma separated. They actually don't need hardly any of the metadata that you see in a full-blown sample sheet. Basically, lane, comma, sample ID, comma, sample name, comma, sample project, comma, index 2. The lane is just whatever the lane number is. The sample ID is whatever. Sample name, I would generally recommend always making exactly the same as sample ID. The project is just going to control what directory the output files go into, just to kind of group output files easier. And then the index and index 2 are the target MER for the first and second index. And if the second index, if it's single index, you just leave the second index column blank. You can probably leave off that whole column, but I just always have to keep this header the same and just leave a blank column there. There's no need for the Illumina IEM experiment manager. There's no need for complicated spreadsheet templates. The characters you're allowed in the sample names and project names are very limited. You get uppercase, lowercase, digits, hyphens, and underscores, and almost nothing else. So, don't, sometimes people do dollar signs, whatever. It just doesn't work. Anything else I need to say there? Oh, yeah, I do have some recommendations for those names. Like ideally, your names might end up being something like this. A project might be named like this, and a sample may be named like this. And there's reasons kind of why you want them like that, because you kind of want them to be globally unique when you send them to NCBI. That'd be kind of nice. and you kind of want them to be sort of self-descriptive and have all, kind of all the relevant information. So like the project, you kind of want to say institution, maybe PI, and then maybe the person actually doing the work in the lab. And then maybe some description, maybe the year, and then maybe some description of the project. Like maybe this is High C for 2023. Doe is some grad student in the Smith lab at UCLA or something. The sample names, I highly recommend that the first part of the sample names be completely related to the physicality of what happened. Do not try to put the first part being the interpretation of what happened. So that means sequencing core, institution, sequencing core, identifier for the flow cell, identifier for the Demux target, just literally the MER that was used to target this. This is an unambiguous identifier. It's not contaminated by by possible errors in interpretation, because what happens sometimes is that if your interpretation is, oh, this is wild type 8-hour rep 1, but then when you're 3 months into the project and decide that there's no way that's possible and 2 samples had to be swapped and now you got to rename things, you will then have files before the renaming and after the renaming, and you'll never know after that point which one you've got, and it's very confusing. That's why the physical ID, this kind of stuff, never changes, and it's unambiguous. And if you have to change this part, whatever, but this is always canonical and definitive, right? So this part, this pile are the reads that responded to this Demux target, right? That does not depend on what you interpret those as what sample they're from. And so that's why I kind of recommend this kind of format for the sample names. But of course, people hate these because you can't tell what this is unless your memory is like amazing, right? If you're Rain Man, I guess maybe or something. But so you do want the kind of human readable name there. But yeah, just tack it off at the end where it's kind of like just a hint or something secondary. This is the real identifier. Anyway, people name things however they like that. This is just a recommendation. Okay, so we're about to start R, where we'll do some interesting things. R will have 2 goals, basically. R is where you're basically going to figure out what the correct Demux tolerance should be. And R is going to be where you would figure out what mitigations you would do to rescue any samples that are in trouble, basically. In terms of tolerance, that barcode mismatches parameter to BCL2FASTQ2, the only options it can take, 0, 1, or 2. Furthermore, 0 is always an option, exact matches only. 1 allows 1 mismatch, but you can only do it if the sample sheet that you give to BCL2FASTQ2 has all targets at least 3 mismatches apart, because we talked about that on day 1 where the little white circles can't overlap. To do 2 mismatch tolerance, your minimum target distance in your sample sheet has to be 5. Okay. That's not too common with most kits these days. Not if you're at like 7 MERS or 8 MERS or something. Most of the kits down there go for higher plexity. They don't even optimize for maximum distance, even at the plexity they have. But anyway, some of the kits out in like 11, 12 MERS and so on, those have a chance of being 5 apart or something. Or if you're doing a really low plexity, just happen to just chosen the indices that are really far apart, you can get a 5+ mismatch. But anyway, usually this is the most common one that you run with. Usually if you're here, you're already in a suboptimal position, right? Somebody mixed guys that shouldn't really have been mixed or whatever. But anyway, yeah, so the rescue, we talked a little bit about on day 1 this, the rescues that you do often involve playing games with a sample sheet. Like we talked about how you may like introduce extra targets for a guy that capture some of the further away corruptions of him that happen to be high frequency. Or you can do that off-center targeting trick where maybe you have 2 guys whose centers are 2 mismatches apart. The lane needs 1 mismatch tolerance. So you intentionally lie about one of the targets 1 mismatch away so that they're 3 mismatches apart, enabling 1 mismatch tolerance. But then because the off-center guy is only 1 mismatch away from the real center, it's still the 1 mismatch tolerance will still suck that into that off-target collection. Anyway, so those are the kinds of rescue tricks you do. R is going to how you figure out the details and so on, but that's kind of the kind of things you do. So my directory and Hoffman, where all this stuff is world readable. I can't give you the raw run folder for ZBP099 because I don't have permission from the lane owner to do that. But most of the files here are world readable. You can grab the raw run folder for 098, which actually has both lane 1 and lane 2 data in it. And then most of these index files and sort of summary data that we're producing here, and which will serve as inputs in R and so on. They're all here. You can copy them out to your own account, copy into your local machine, whatever. If you want to follow along the next part where we're in R, then you can do that by having, like, basically what are you going to need? You're going to need the index histograms and those lists of what we decided were the indices, the targets that are present. Okay, so that's 10, we're at 10:20, so maybe we take a break here because it's you know, supposed to take a break at once an hour. But when we come back, we're starting the R. We're going to analyze the histograms in R, basically. And it's nice because we'll get a lot of information from that. Way more information than you can get even by running BCL2FASTQ2 many times. It's just, the R is going to be pretty quick and give us a real detailed picture about what would happen if you were to vary Demux in various ways. Yes, so the 098, which is the one we're talking about right now, that is world readable. It is this directory here. You can copy this whole thing. You would do something like copy recursive. The V would give you, maybe it's capital R, and the V would give you progress information once per file. And then the source place would be my scratch directory. And this is the name. So that's the from. That's where we're copying from. I'm just going to put a lot of spaces here so I can line up the two guys here. This is now the destination. So now this would be, you know, what's your Hoffman name? So you're like something like this. Something like this. Well, you know, whatever. Okay. So this is your scratch space, right? Your home directory probably doesn't have enough space. Those are pretty tiny. So this is your scratch space, and now you know, just, you know, call it whatever. So this is copy recursive. Recursive means not just the thing I named, but the entire directory tree at that point. The V I told you will just give you progress information, so you'll see the files as they go by, so it doesn't just sit there for a long time looking like it's not doing anything. And this is the from, and this is the to, and that'll grab you a copy of that raw run folder. Yeah. There's my R. I guess we're gonna have to make R bigger. Should we turn the lights? I mean, is it like the screen brightness or whatever? I guess you're all looking at your screens anyway, so it's, yeah. Oh, you want to see the copy command? Yeah, it's without the control C at the end, but anyway, this stuff. Well, whatever. This just names a directory, and you got to say where you want to put it. If the destination doesn't exist, it assumes that
this directory becomes the directory you did that doesn't exist yet, and so it'll create that in that place. If this destination already exists, it would put a new directory of the source name there. Put it there. I mean, I don't know where you're going to put it. You probably got to put your scratch page because most of us have the home directories are very tiny, and if you have any project space, my experience is always full, like 100% full. Like an MCDB group, I don't know, we have like 12 terabytes or something, and it's like 11.9 T full, always, like forever. So I mean, basically the only place I can find you can ever do anything in Hoffman is scratch. Usual mode of operation of Hoffman then is you have to have your data always locally. When you're about to do something in Hoffman, you copy all the data to Hoffman scratch, you work on it, then you copy the data back up. That's the way I always end up working. No permanent storage on Hoffman, as far as I'm concerned. Yeah, so they used to really do that, but I haven't seen it happen in a few months now. Yeah, but it, you know, you don't want to rely. You don't want to rely on that because we have totally had grad students and stuff that like worked for like 10 months in Scratch or something, and then just when like then they did like the maintenance whatever, and it all disappeared, and now it's like.
Well, yeah, that's so. I want to try to do all this stuff that we have a different university. We did not have this Scratch that it was just.
You had to use You had to use whatever storage you had, and it was full. It was full. Oh, you had plenty of storage.
Yeah. And so when I came here, I was like, "What the hell is this Scratch nonsense?"
Yeah.
Do you know why they went with this system? Like,
Well, because somebody has to pay for the storage at some point, right? And some users want 100 T, and some users use like 0.1 T.
I guess.
And so campus cannot afford to buy in. Campus cannot just satisfy everyone's storage desires like blind. It's just. You got individual undergrads that probably could fill up 100 T just because of like their movie collection, or I don't know what they download these things, but you know.
Usually buy the storage, but it's just hard to maintain.
Yeah. So the problem is that storage files never get deleted, right? First of all, people leave campus, but then the PI doesn't want to like just delete all that because the project's in there somewhere. I mean, but then the person responsible for the data is gone, and so, and who's going to put the time in there to sort the files and decide which ones are important, which ones aren't? And so basically, the eternal problem is storage only accretes, right? Never goes down; it goes up, and since the ceiling is finite, eventually it fills. And until you buy more, it's full. And I don't know. I mean. I don't know how much money we were paying the Google Drive and Box and whatever. Because at some point they had to cut it off because it was getting insane. And I think some people have been grandfathered in at insane levels. But it's just, storage costs money is a problem, and it's a finite resource. So how are you going to allocate it? So Scratch is the solution. It's the open field that just gets nuked once in a while, so it can't accumulate. That's the only solution we seem to have for accumulation. Is we'll just turn it into a glass parking lot once in a while. Start over.
I'm still wondering for all this is involved, how far do this go? I know you have like.
So I have the BSCRC is holding currently about 380 terabytes, not on Hoffman, of course. Those are with super micro drive, like chassis that hold like 40 drives at a time or something, with like some RAID cards and some servers we have in our own space. And the oldest of those machines is probably like 10 years, 12 years old, and so on. And so those drives could die at any point, right? And so on. But so I don't trust those for like new data. But until they really die, I'm not going to kill the old data. And so a couple generations of that, and that's how you end up with like a third of a petabyte hanging around.
So you still have like.
I haven't had to throw anything away yet, but I'm like really, really there now. I no joke now.
Is there a solution?
Is there? Yes. Yeah, here. Yeah, okay, I guess we should go back to it. We should continue again. Yeah, I have no storage is a mess at home, you know, where I have like a 50T thing that I threw together. Storage is a mess at work, storage is a mess in the cars, storage is a mess on Hoffman. And it's just because data life cycle and like data importance and like going through old stuff, it just never happens. Very difficult. It's like too expensive to throw the data away, but also too expensive to buy infinite amounts of storage. So I don't know. You know what some people do for their sequence of storage? Get the publication out, send it to NCBI, SRA, and GEO, and that's where you pull your own data from NCBI. You can totally work that way. You can even deposit stuff in GEO and SRA pre-pub, you know, so you know pre-publication. So I have no idea what NCBI is doing inside these days. I mean the storage they need is petabytes and petabytes. I don't even know what's happening inside there anymore. Well, I think they're all using Amazon and Google and stuff with very special agreements and so on. They're like some of the largest customers. So.
I don't know. I will say, I would have loved it if they'd explained all of this much better with the sign up.
So you know, another problem is that like in some sense storage is cheap. Go to a Black Friday sale, get a 16 terabyte USB 3 disk for like $250. You don't need many of those, but for your personal needs are pretty well covered, or a small lab's needs are pretty well covered. The problem is that it's not really a great form of storage, right? Because it's one disk, it can die, it only connects to one machine, it could be kind of slow. It does, you know, so you know, but if you want kind of like high performance storage, well, now you're talking 10 times, 20 times the price per terabyte. Not so cheap. So it's not like a I don't know, complicated problem. Okay, so we're gonna do R now. So you may like R Studio or whatever. I'm just gonna use kind of base R with the base GUI app that comes on the Mac with. I'm not gonna really have time to completely explain all the R code in here. I'll just kind of point out some highlights and stuff, but you know, we're less important to understand totally how the R code works inside than what it's doing. Okay, so this first function we're gonna define just is a little thing to make things kind of prettier. It just composes names with zeros padded so that the you know one of the great computer problems is, you know, when you sort things by strings, it's like, are you sorting it in dictionary order or are you sorting it in numeric order, right? Because like in the dictionary, you compare first character to first character and keep going until you find a difference, and then the character that comes first at the first difference is the one that goes, the string that goes first. You know, so like AB comes before ABC. But for numbers, integers written as strings doesn't work right? So like if you do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you sort it as strings, you're going to get 1, 10, 2, 3, 4, 5, 6, 7, 8, 9. So the way to kind of make it always happens in bioinformatics. You know, it's like essentially the only way that kind of really makes the two worlds the same. Just zero pad your integers so they're all the same length, right? Then the two sorts work the same. And so that's, you know, chromosome numbers, integer coordinates and things. I usually try to zero pad most everything. It just, you know, files, you know, everything just sorts the same way, then you don't really have this issue. This little function kind of is doing the same thing. Here I'm asking it, give me ABC 5 to 10, and it figures out that, oh, 10 needs 2 digits, and so I have to zero pad the 5 to 9 and whatever. So it just gives you a list of the strings from there to there, kind of zero padded. Anyway, so that's just going to make some of our tables have row and column names that are a little prettier. First thing to do is we need to read in the histogram into R. So this is not going to copy and paste for you literally until I tell you a little thing, but I'll show you. I can just paste it. And that actually read the file right out of Hoffman. So I did not even have to copy it. I've made sort of like this little poor man's network file system here using this little trick. And essentially what we did is we just had R execute the SSH command to Hoffman, on Hoffman run the cat command, and then we gave cat the path name of the file we wanted to produce. And so this SSH command that runs on my local machine, but then which calls up Hoffman and runs this cat command over there, just basically spits out the output of that cat command, which is the contents of the file. And then the paste 0 is just here so that I can break this long string into two lines on the slide. That's not really essential. What's the magic here is the pipe that wraps around it. And that tells R that the string I'm passing into this file related function is not to treat this argument as a file name, but as a command to run and then to read the output of that as the input to this read table. And so that's the little magic here. So if I were to take this SSH command and just paste it into my local terminal, you'll see that I'm just going to get a copy of the file out. There we go. Because I have passwordless SSH login turned on, that's very convenient. And all we're doing, telling R is basically start that local command and take whatever output it produces, and that's what read tables can read on. So if you don't have all that machinery ready or whatever, you would just replace this with just the local file name that you gave the name of the index file, whatever. That would just, you've used read table before, I'm sure. In R, it's usually one of the main ways you get data into it. But this is kind of cool. Basically, it means that I can pull small files off of Hoffman Live. Very convenient, really. So anyway, so that's basically just a little trick, not an essential trick, but otherwise you got to copy the file to your local machine and give the local path name. Here we'll just make some pretty row names, and then I'll show you the head and tail of this table. I mean, the full table is 25,000 rows without pasting it in the wrong place. Always a great thing to do in any command line thing. Okay, so there's the head and tail. It's got 25,697 rows because the file has 25,697 rows. And I'll go back to the slide because it's right here, that head and tail. And so this is really just the 2-column index file that we made as an R data frame, which is a very convenient way to have data in R. And we have actually got like the columns labeled MER and tally, and we've actually got the histogram entries numbered. This is histogram entry rank number 1. This is histogram entry rank number 3, and so on. So we've got a nice data frame that's very pretty and labeled and so on, ready to go. We'll also need the list of 21 target indices that we decided were empirically present here. I'll do another read table with the poor man's file system here to suck that in. Okay, that's of course a very small file. And that actually reads as a data frame, but this is really just a list of strings. We'd rather have it as an R character variable, so we'll convert the format to that. And then we will attach some row, I guess they're column names. Maybe they're column names, I guess, there. So that is just the 21 guys that we chose. They're actually currently in the order they're currently in is by descending frequency, which and that's maybe kind of nice. And we're just going to call them C01 to C21. Okay, just canonical target C01 to canonical target 21. Okay, so that's just importing the data into R. We're going to need some libraries. We need string disk to compute Hamming distances, how many mismatches there are between two strings. String disk will do that kind of stuff very easily. Hopefully you've seen the tidyverse before, dpiler and tidyr. Those are great to be familiar with because they allow you to do very sophisticated data transformations very easily. The syntax is very easy. You'll see in the slide or two how we're going to use that dpiler and so on. And then we got this blob of text here, which is basically going to implement a complete Demux pipeline in R that is more flexible than BCL2FASTQ2 and way faster and uses almost no RAM. So this is very nice. I will paste that and run it. And you'll even see we even get a little text progress bar at the bottom there. And so we know we're already 10% done. And we can kind of look here, what are we doing? Okay. We're going to augment the histogram with 2 new columns. So we first create those columns and just load them up with -1s. Just doesn't matter. We just blank values, placeholder values for the 2 new columns. This blob here and this blob here and this blob here are the text progress blob. Not important, it's pretty. For silly reasons, R does not handle empty tables well. So if it happened that the histogram was empty, this for loop wouldn't actually work because 1 to 0 doesn't do the right thing in R. Usually a good defense in R is always wrap your formulas with sort of the 0 test. So only do this if there's at least an entry in the histogram. You're never going to have a histogram that's empty here. It's this if is really pointless, but whatever. The main loop is here. We just do a block of code for every row of the histogram. We pull out the MER and H, and then we compute the distance, how many mismatches away H is from all of the canonical targets. So string dist matrix comes from that string dist package and takes the string that you want to start as the comparison, and then a list of strings, which is what you want to compare them to. And then we're telling the particular distance measure we want to use as Hamming, which is simply number of mismatches apart. This just makes it a little faster because we don't have any like fancy Unicode characters in there. Everything's just ASCII, ACGT, and very fast. This just makes it faster. And then this just produces basically a vector output that's just the list of distances. So it's distance 3 mismatches from target 1, it's 7 from target 2, it's 5 from target 3. This is then the closest distance, the smallest distance. This is then which targets attain the closest distance, the indices in the list of targets that hit that distance. And then the way we're going to do it is that our rule is what we talked about in day 1, which is that if there are multiple targets at the same minimum distance away from you, that's Demux fail for this process. Ambiguous, don't know. And we will use, we've got 21 targets, we will use 22 as Demux fail. R is a very 1-based language. Some languages are 0-based, but R likes to count from 1. So we could call Demux fail like 0. That's essentially going to shift all the rows down 1. We really want row 1 of things to correspond to target 1. So it makes more sense for us to put Demux fail at the bottom. So we will number Demux fail as 22. And if there's n targets, Demux fail is n plus 1. And so what we do is that if there are multiple guys at the best distance, then the pile that we put them into is n plus 1, and otherwise it's the unique. Otherwise, there's only one guy in the best. There's only one guy that hit the best distance, and the Demux pile that he goes into is simply what that one guy is, and so on. And then basically we've now computed all the data we like. We keep track of the closest distance and what Demux pile it goes into. And that's what our 2 columns are for. And so we just record what we just computed there, and that's it. And this has been done for a while where we've had that discussion. That essentially demuxed the entire lane with arbitrary demux threshold tolerance with almost no RAM and in like a minute. So this is very convenient. Okay, so let's look at it. Okay, so we put the result back in HI1, histogram of index 1, and it has just 2 new columns now is the thing. So let me do a little bigger head there so we can see, what is it, is N how you tell it more? Yeah, okay, so that's 20 lines. It's the default, what is it, 6? 7? 6, that's a weird choice. Well, I need to go to like 30 because remember the top of our guys is essentially all the 0 mismatch perfect guys, whatever. So I want to see a little bit into where we start getting the mismatch guys. So here's our histogram. Here is the closest distance to the targets. Well, remember all these guys at the front are the targets. So yeah, closest distance is 0. And which target attains that closest distance? Well, we've also arranged that our targets are in order of descending frequency by exact match. So that's why the Demux pile will just count basically up to 21 here. Well, except for this number, remember this one guy that was like the one mismatch systematic error of number 19. So you see that here. This entry is 1 mismatch away to number 19. And then this guy, phi x, is really the target 21 at 0 mismatches. And then down here, this is 1 mismatch to target 16, 1 mismatch to target 5. We're going to have to go a little ways before we see somebody that is an ambiguous guy, I guess. Let's see, is there any ambiguous guys in the top 200? Yeah, I guess so. Here's a 22, right? So this guy is seen 14,906 times. He is 4 mismatches away from multiple things in the target list. And so he goes into Demux fail at pile 22. So that's cool. That's a lot of information. We'd like that summarized in various ways. Maybe we'll just play around, make some plots first. This is sort of a silly plot to make, but here we're just plotting in the rank order of the histogram what that mismatch distance is. little hard to see what's going on here because it's a scatter plot with a zillion dots. We should really do this as a density. And in fact, in the next slide, we turn that into a density plot. And what do you see? At the very top of the histogram, of course, you see things with very low mismatches. But then as you go deeper into the histogram, the number of mismatches that is going higher. This is exactly what you'd expect. As you get rarer and rarer, you're actually getting further and further away from the targets. Here, we're just seeing which library is the closest. And of course, it's just going to be all of them all over the place, right? It's not like all the libraries, like library 1 is going to have all of its variant MERS, including the rare ones, all at the front. No, they're all going to be intermixed. So this got to make sense. And of course, why, when you do the density plot, why is Demux fail? This is 21, that's 22, that's Demux fail in this top row. Why is he the brightest? Because by this plot is not weighted by frequency. This plot is weighted by distinct MERS. And almost all distinct MERS, as we saw when we looked at the bottom of the histogram file, are very low frequency, 1s and 2s. So, and they're going to be very far apart from all the targets. They're just kind of the random, just random stuff. And so by number of distinct MERS, they're almost all Demux fail. It's just that there's a few guys where it's all concentrated, and that's where all the meat goes. You can make these plots in various ways with log axes, not log axes, whatever. These aren't really all that interesting, so I'm not going to really elaborate them. I want to move on to the next stage where we summarize the data that we just generated in a more useful form. And here's where we're going to start using dplyr with these they're kind of like pipes in the shell. Okay, so when you have this percent greater than percent, it means that the thing that starts this is the data table that starts the whole process off. And then sort of each one of these guys establishes a flow where it's sort of like you start with this data, and then that's the thing on the left is the input, and the thing on the right is some transformation or whatever. So you start with this table, and then you're going to do something to it, and then you're going to do something else to that result. And we're kind of piping the table around. And so by the time we get to the end here, we've done a whole bunch of transformations on the table. And then that's what we save in a new variable hi1 demux summary. Okay, so what transformations we do? Maybe I'll show you the output, and then we'll kind of go through how this transformation is achieved. So let me just run this code, and we'll just look at the output variable that we get. And what we get here is a summarized matrix that's packed a whole lot of information into a small space. I guess it's a little bigger on this part of the screen, so I'll show it here because it's just physically larger font. What we have is one row for each target, and then the bottom row is for Demux fail. So essentially, these are the Demux piles on the left, the rows. In the columns, we have mismatch distance. So MM0 is for 0 mismatches, exact hits. MM1s are for things that exactly 1 mismatch, not less than or equal to 1, exactly 1. MM2s are exactly 2 mismatches, 3, 4, 5, and actually you can't really get beyond 6 mismatches here, just because the length of our guys and the data and so on. And what you have here then in the intersections is the number of index reads that fall into that combination. So there are exactly 108,713 index reads that uniquely demux to pile target 1 and are exactly 2 mismatches away from target. Okay. So like suppose you were to demux with less than or equal to 2 tolerance. How big would the demux piles be? You just add up these 3 numbers in each row. This is the exact hits, mismatch 1 hits, mismatch 2 hits. If you add those up, that would be less than or equal to 2 tolerance. So the cumulative sums of the rows here would tell you the size of the Demux piles as you were to vary the Demux tolerance, including to tolerances that BCL2FASTQ2 can't even do, right? So this is a great piece of information here. I'm a little torn whether we should say how we get that. We'll just briefly kind of describe how we made that transformation, right? Remember what we started with, right? What we started with is this augmented histogram, right? So there's our histogram. So that's the augmentation Demux analysis we did. We're changing this thing, which is sort of a 1D view, into this kind of 2D view. How did we do that? We first added these first two transformations are a little hard to explain. They're related to the fact that we don't want any holes in this matrix. Like if there was sort of a 0 column, you might lose like the mismatch 3 or something. These just guarantee that the mismatch columns go from 0 to something with no gaps in between. Very unlikely to really be necessary, but this just guarantees that sort of the matrix doesn't have any holes in it. Don't worry about those so much. The next one is very one of the very powerful features of depiler, which is group by. And what depiler can do with group by is that instead of treating the input table as a list of rows, it can treat it as a list of sets of rows. The grouping variable decides the sets. So you can collect rows that share some property together in a set. And now the table is kind of broken into these little chunks, and then you can do operations on the chunks. So what is a chunk for us? It is the combination of mismatch distance and what Demux pile you belong to, because that's exactly the row and column that we want the output to be structured as. So to get this number, I had to go to the original table and find all the rows that share that Demux tolerance to that Demux pile. It's exactly what the group by is going to group by. So this tells depiler to sort of reorder, kind of introduce a new level of structure to the table, grouping all the rows that will land in the same output place in the same place of the output matrix together. So then the next transformation is summarize. What summarize does is it operates on the groups, and it uses the numbers in the group to compute some summary number for the group. What's that going to be for us? It's simply going to be to add up the number of reads, right? It's just to add up the tallies. That's what the number we want here is. Once you've decided what rows of the original histogram belong here, we just want to add up the tally and find out how many reads belong here. So the summarization is that the new tally value, each group is now going to be replaced by a single row. We're summarizing, right? So the new single row for each group has a column called tally, which is simply the sum of the column that used to be called tally in the individual members of the group. That's exactly what we want to do. That's what constructs these sum numbers in this guy. We can then ungroup. We've done the summarization now. The histogram is now still a one-dimensional structure after the ungroup, but it's been summarized that now it just has sort of like, kind of like the columns are now the row number of the output matrix, the column number of the output matrix, and the value that goes in that row column. So now we've kind of got the output matrix. It's just written as like row index, column index, value. And now we actually just want to literally arrange it in like a matrix and not have all the indexing. That's what the next thing does, pivot wider. So it's a little hard to explain the syntax here, but essentially exactly what's going on here is exactly that. Pivot wider, you can tell it, oh, these are row indices, these are column indices, and these are the values. And I want you to go from the linear representation to the array representation. And after the pivot wider is done, it turns out there's a column we don't need anymore. And so this select with a minus means delete the column of this name. So that just gets rid of a column that's done its job we don't need anymore. I forget what kind of R structure this produces as output, maybe a tibble or something, I don't know. Anyway, as matrix turns it into an R matrix, which is really kind of the data type we really like to have this in. The column names and row names, we put I think what comes out of this has almost no row and column names anymore. Depiler and so on really take the idea that the row and column names are harmful, and they'd rather just have those be extra rows and columns in the real data table and not have sort of like these special row and column names. But actually in R's world, base R, the names are generally helpful. And so we put them back on. So we enable the rows by the target names, and we actually label this, the bottom one is Demux fail, so it's really obvious. And then we construct these DMM0 and so on for the row names and so on, and then that's it. And so there we go. And so that's this very nice matrix. And so now we can visualize this matrix a little bit. So for example, one of the important things that we can tell from this is that, like, you can just look at this and see that, for example, one mismatch tolerance is important for some of these guys, right? Because here's the 0 exact matches only. This is if you were allow this is the additional recovery you would get from allowing one mismatch tolerance. Well, for a lot of these guys, it's like, this is what, 30 million and this is 300,000. That's like a 1%, not a big deal. But you can kind of just look down and see, oh, number 5 is quite a bit bigger than that, right? He's about the same size as everybody else, but he has 4 times more benefit from one mismatch. And that's nothing compared to our favorite number 19, where it's 14 million and 6 million, right? So it's very clear here that sort of one mismatch tolerance is a very kind of minor benefit for most of these libraries. But for library 5 and for library 19, especially library 19, that one mismatch tolerance is really important. So we could actually make some R plots that kind of make this a little more explicit, right? So we could, let's just make keep track of to turn things into percents and stuff, we need to know how many PF1 spots are in the lane. You can just add up all the entries in this matrix to get that. We'll need the, if we want to talk about Demux tolerance being less than or equal to something and not exactly equal to something, we'll need those cumulative sums of the rows of that matrix. So we can do a cum sum here to kind of get the sums there. So we'll do this, and that gives us, this is actually collapsed over all the samples. So this says that if you were to allow 0 mismatch tolerance, 96% of PF1s would be successfully demuxed to something. If you go up to 1%, one mismatch tolerance, 99% of PF1s go to some pile, and so on. And what you see here is if you do a plot with that, so that's this plot over here. I think we're supposed to add the names. No, I'm not sure what oh, I guess it already had the names attached. I guess that's redundant. But this plot here, that's this one shown in the slide here. This is essentially average, total lane recovery. This does not show per sample yet, but this shows the overall recovery for the lane as you increase the Demux tolerance. And what do you typically see? You typically see a plateau is reached. You generally, because you know that the further right you go, the more likely you are to have missed Demux, because you're increasing the Demux tolerance to sort of crazy levels. But you also know that at like 0 tolerance, you're probably going to lose some. Like we know like this number 19 guy is like 30%, we just want to make it tolerant. So you kind of want to go a little bit to the right to get most of the benefit you're ever going to get by increasing Demux tolerance, but stop as soon as you sort of are in the plateau, because you don't want to like increase the missed Demux any more than you have to. And for this one, it looks like, yeah, it looks like one mismatch maybe is where it is, right? Most of the benefit you're ever going to get from increasing Demux tolerance is had at one mismatch. And, and that gets us to what, 99% of PF1s went to a pile at that point. So that sounds great. So yeah, that sort of votes for one mismatch, looking at the lane overall. This other plot is the per sample view, right? So we can do this, this plot. There's the what's here is the textual form of the plot, and then this is the graphical form here. And so what this says is that this is target 1, 2, 3, 4, 5, target 20, target 21. 21's phi-x, I think, and 22 isn't here because that's Demux fell. It's not a target. And what's the y-axis here is the fraction of less than or equal to 1 mismatch recovery that requires the 1 mismatch. Right? And so this makes it very clear. Target 5, maybe about 4% of his recovery, depends on that 1 mismatch, but target 19 is more than 30%. In fact, if you look at the textual form, we can say it's 32.1% of his recovery depends on 1 mismatch. 32.1% of his less than or equal to 1 mismatch recovery depends on the 1. You would lose it if you went to 0 mismatch. Anyway, so you can see now how you can sort of start to make more intelligent decisions. You're actually seeing kind of the picture overall now and on a per sample basis. So this next slide is just annotate what we just talked about, annotating the slide there, so you can figure it out when we're not talking about it in the moment. The slides try to stand alone if you were to read them even without coming. Yeah, so we kind of talked about this thought process too, where it's like, we're accumulating more and more evidence where it's like the answer for this lane is 1 mismatch tolerance. Now let's do some thought experiments here to kind of show you how you would handle situations that didn't happen to arise here, but could have easily arisen here and would cause problems for the blind Demux approach, but now we have good visibility into things and we know it's here. So here's the start of a thought experiment. Suppose we had been forced to exact only Demux because somewhere in the targets there's a 1 mismatch or a 2 mismatch conflict, right? So that could be maybe, remember phi-x wasn't in the sample sheet. Well, maybe they just were unlucky and one of the indices they chose from their kit happens to be a close hit to phi-x, and then you'd be in that situation. Or maybe the mix is slightly different, or you're sharing with somebody else and you had a 1 or 2 mismatch conflict with them. So your BCL to FASTQ2 options now are basically exact matches only. Okay, so you're now in the exact matches only situation. You do this and you realize though that number 19 really wants one mismatch, right? So what can we do? Well, we kind of, because of the earlier assumption, we can't increase the Demux tolerance. Well, so now we're in, what kind of remediations do we have available to us? Well, one of them is add a variant MERT, an extra row to the sample sheet that specifically targets this high frequency corruption number 19, and we'll pull it back. But how do you find out what sequence to add or what set of sequences to add? We've got all the data right here in R ready to go. So first of all, we can figure out what the recovery from number 19 is with less than or equal to 1 mismatch tolerance. Oops, I keep wanting to place it there, but it should go here. So if we look up in that matrix, C19 exact matches plus C19 exactly 1 mismatch, that's how many reads you get with less than or equal to 1 mismatch tolerance to C19 using all 1 mismatch variants of them. So, if you were to really do a full 1 mismatch tolerance, that's how many would come out. Okay, but we can't afford a full mismatch tolerance because how many MERS would we have to add to the sample sheet to attain a real simulation of full 1 mismatch tolerance? Well, we can look at how many entries in our augmented histogram point at number 19. So how many point at number 19? And the answer is 543. Now that's allowing any Demux tolerance whatsoever, but we know we're going to say, okay, well, just Demux tolerance up to 1. So how many indices go into the 19 pile and are less than or equal to 1 mismatch away? Still 28, one of which is the exact match. So you would have to add 27 rows to really simulate in an exact mismatch, in exact Demux. You have to add 27 rows to simulate the one mismatch tolerance. That's more than you probably want to add. But the question is, okay, but what does the frequency of those look like? Are most of those so low? It doesn't matter. How few can we get that list down to know what to add? So we can actually show me all the entries in the histogram that demux to number 19 with less than or equal to 1 tolerance, right? We'll just pull out those rows from our augmented table. And here you see them. Here, number 1, of course, is the perfect match. It's this guy. And here are all the 27 guys that go to pile 19 with exactly 1 mismatch. And you can see their frequencies here. And you can see right away, well, if you were to pick one, you pick that one. That's what it is. That's your target to add. Maybe if you want some more, you pick this 460,000 guy there. But then it's really kind of petering out pretty fast. And we can ask, we know what perfect 1 mismatch recovery would do. It would do this. So if we were to add just this one variant, how well would we do as a percent of what's possible at all, right? So we would do 100% times, this is what we would get with the single variant. And this is what we could do if we had all the 1 mismatch variants. 97% of what 1 mismatch tolerance would do is achieved by adding this single variant. That's your answer. So this is how you actually don't have to guess what to do to the sample sheet. You can just figure it out directly, whatever the situation is. Okay, that's kind of a lot to. I'm not going to really be able to show you every possible kind of like situation that comes in. So but I kind of just want to get you in the position where sort of like you have the data in front of you, and whatever situation you actually were in, you can kind of use your own logic to work it out. Once you have the data in front of you, you can kind of figure out your situation. If you don't even have the data, then you're kind of blind and you can't do anything. But at least kind of like with a logical mind and with the data in front of you, whatever situation you're in, you can kind of work through. That's kind of the goal of talking about this kind of stuff here. So all this is kind of like what we just went through in words, but when you look at this in a week or a month or a year or whatever, the slides here, hopefully this jogs your memory or something in terms of the logic here. Anyway, so that gives you, now you, without actually having to go through a real example that involves some remediation, you now see kind of how remediation would go. This the one example can kind of serve multiple purposes, even though really as itself, it's actually a pretty good run, but you can easily see how it could have been different. So, how could you end up in a loading situation? You could have had somebody throwing a spike in that just happened to be really close to one of the guys already there, and you'd be in the situation where that little spike in of piddling million reads or something is now going to cost you many millions of reads from the other guys because the tolerance went to 0. But anyway, even in a situation where your tolerance is forced lower than you want, you can still claw back by doing these kind of like variant additions and stuff. And this kind of approach in R allows you to actually figure out a small set of variants that you could add that achieve almost all of the gain. Okay, so we've basically completely done the bottom-up approach on this example. We are now ready to compose the final sample sheet. Okay, and it's a file, it's a plain text file that looks just like this. You can argue about what the read and project names should be, different styles for those. Here, I think this is the file. Oh, not this, not with the cat there. Okay, so there's the file name, and if you look at this file, there it is. That's the complete contents. Of course, the names, the project and sample names I've chosen are quite long, so it kind of looks messier than it is. But this is just a comma separated file. So if I highlight the commas, there you go. Here the columns are kind of colored to make it a little easier to see. Red is the lane. The oranges are 2 copies of what are the sample name. As I said, I really recommend you make the sample ID and sample name exactly the same. The yellow is the project, and the purple is the actual sequences. And relative to the user sample sheet, basically the only thing we really did here is we added phi-x. That was essentially the only correction that was really needed. But if things had been different, if we had one of these close conflicts and we had to do the variant addition or something, we'd have another row in here, which would be the high variant of number 19 to claw back his 6 million that would otherwise lose. But yeah, anyway, so I named phi-x here just kind of in a similar pattern to the others. That's typically what I do. So for example, the index SMR is in here, so that's of course poly G. And then rather than associating to project 1 or project 2, phi-x is really a property of the mixture of the flow cell itself. And so I don't put him in either project 1 or project 2. I just call him part of the mix, right? So the origin of phi-x was at mixing time and not one of the projects. So I put him in the project called just the mix. And his sample name, it looks like all the samples here are like 6 characters. So I just kept the 6 characters. So the kind of the file names all will line up nicely in the terminal. And I just called it dark px phi-x. Just, sometimes I just call phi-x p if I only have a character, px 2 characters, 3 characters, phi 4 characters, phix, 7 characters like phi-x. Anyway, whatever. I mean, yeah, this is all just minor stuff. It doesn't really matter. But, so that's our final sample sheet. We are now ready to run the ultimate BCL2FASTQ2 run. We have a quality assured sample sheet. We've really kind of done everything that you could do to kind of look at the Demux level of this lane. And we are ready to do the final Demux FASTQ generation with one more BCL2FASTQ2 run. What does that look like? Command line parameters look almost exactly the same as the non-Demux run. What changes? We can drop the command line parameter, create FASTQ for index reads, because we no longer need the I1 files. We don't need the index reads anymore. They actually will get, if you remember the FASTQ file format, there's that one column that was 0 for a lot of our reads because we were always looking at pre-Demux stuff. Actually, the index reads, or at least the ACGTN portions, the Q scores are lost, but nobody really cares about the Q scores for index reads. They'll actually go into the read names. You'll see that in a second, but we kind of aren't even going to, if we don't even ask for the I1 files, we still kind of got the important data in there. They're going to be embedded into the read names. Of course, the sample sheet dev null goes away. The biggest change is simply in the sample sheet parameter, we now give the file name of our ultimate sample sheet here. That's the big change. And of course, the other thing to pay attention to is that now the barcode mismatches parameter matters, right? And we decided 1,000 ways that this is a 1 mismatch tolerance lane, and so we put a 1. And the use basis mask, that didn't really change here in this example, but if you had UMIs, it would change. So there's actually a couple ways UMIs get handled, but the way we usually handle them is, remember the UMIs, like if you have like a first index is an 8 plus 8 base, 6, if the first index was 16 bases, and only the first 8 bases are used to make the Demux decision, but the next 8 bases are these randomized molecular identifier, then Demux, of course, only needs to pay attention to those first 8 bases. But if you do like I8, N8 here, the UMI bases are going to be lost forever. They have to go they haven't been used yet because that's a downstream property. The use of the molecular UMIs to deduplicate the lane is something that happens after Demux. And so whatever process that is has to have access to those base calls. They have to survive somewhere. And usually the way we do it is that we actually turn them into sort of a virtual additional main read. So like if you have paired end data, so you have R1 files and R2 files, usually what we do is, since the UMI will be from one of the indices, and indices physically occur in between the 2 main ends, is that what used to be called the R2 file will become the R3 file. So now R1 is SEN, R3 is now PEN, and R2 is the fragment of the indices that is the UMI. And so we kind of pretend it's like sort of like a virtual additional main read. That's usually how we present it. And so you'll have R1, R2, and R3 files. So how do you specify that in the use bases mask? Okay, so suppose physical is 51, 51 paired end. You're actually doing dual indices. 16 plus 8 more dual indices, but that first index, the first 8 is the index and the second 8 is the UMI. So that's like 51 plus parentheses 8 plus 8, which is tag plus UMI, plus 8, that's the second index, plus 51, which is the PEN. And what you want is 51 plus 51 more main ends out, which are now going to be R1 and R3 files. The Demux pile needs to be decided by parentheses 8 plus 0 plus 8, right? Because you want the Demux decision to be based on dual indices, first 8 bases of I1, entire 8 bases of I2. And you want the UMIs, which will be in the R2 files, to essentially be the 0 plus 8 plus 0, right? I mean, you want them to pull out the second 8 bases of the I1. And so the use bases mask that's appropriate in that case would be this. So you would say Y51, that gets you your 51 R1 first main end, comma, because now we're talking about physically I1. I8, which means that indexing and Demux will operate on those next 8 bases, but then Y8, not like N8, you say Y8, because that turns the next 8 bases into a main read, and that creates the R2, comma, because now we're talking about physical I2, I8, because the next 8 bases, which are from I2, are what Demux needs to operate upon because we're doing dual indexing, comma, because now we're talking about physical second main end, Y51. We want those to become the 51 bases R3. And maybe, I mean, hopefully that has some, I mean, hopefully that makes some sense. It really all makes sense if you think about it. Yeah. And that's it. Okay, so this is the long slog. This first round through the full thing is the long slog. So the rest of today we're going to do the paired end example, and that'll go much faster because we've already covered all this bits to talk about.
Not just only for C19, because based on your example.
Oh, yes. You could imagine a Demux pipeline that had a different Demux tolerance per target. I've never seen one. I've never seen one do that. So Illumina that parameter 1, mismatch tolerance, that applies to every target. If you really wanted to do it, you could go to you could tell BCL2FASTQ2 0 tolerance, and just add another row to the sample sheet with the 1 target. I think that's what you're asking. Yeah. So you could affect that if you want. Effectively, you're kind of doing 0 tolerance and everybody except 1 tolerance in number 19.
Right. But so any like case you see for example, you see the C19 is benefit from 1 tolerance, but the other maybe not benefit.
Well, it sort of depends on how afraid you are of misDemux. 1 Demux tolerance usually isn't much to worry about.
Right.
I mean, you can always imagine a situation where anything happens and maybe it doesn't matter, but typically 1 mismatch tolerance is not a problem for misDemux. you know, I mean, unless you had a whole ton of targets that one mismatch apart from each other, then, oh gosh, you know, then it's hopeless at that point. I mean, but you know, if your targets are all 3 apart or more, typically one mismatch tolerance is nothing to worry about for misDemux. So you could do that, but you probably don't have much of a need to do that typically. So, okay. So what is you know, the output from this Demux run is going to be something you're all familiar with, because this is probably what the typical delivery from a core already looks like for you. So here is 098 Demux run. This is the pre-baked one because we lost our connection that was actually running the real thing there. Oh, we haven't even started this command, but you know, here, you know, you get the idea. We're running short on time, so I don't want to do stuff live that we do have pre-baked. So here is what the output directory looks like for the real run. You'll notice that we now have a directory for each project in the sample sheet. The undetermined Demux fail pile will always show up at the top level. And so if we look inside the project 1 subdirectory, we see R1 and R2 files pairs for all of the proj 1 12 samples. And for the proj 2, we see the R1 and R2 pairs for the 8 R2 proj 2 samples. And then remember, we had phi-x, we just put in a project called the mix, because it's not really belongs to either project 1 or project 2. And then there will be a single, I can get a space type, there we go, the single R1, R2 pair for phi-x. And then you see how the naming of these files goes. Here is literally the sample name that's in the sample sheet. But now, like this one is the 10th entry in the sample sheet, so he's S10. But he's still lane 1, main read 1, part 1 of 1. You now understand. You probably some of these things were mysterious. You now understand. I mean, you really understand at a pretty good level now, really how all the files involved in the Illumina work, what the deliveries are really doing, and so on. You know, hopefully hopefully there were sort of there were probably some kind of questions you had you may not even know you had, but they're probably answered. You really have a pretty good understanding of the real details. One of the things you probably want right away after the Demux run is done is just a count of how many reads you got for each target. I mean, we know in R how many we're expecting, right? I mean, we kind of did it already, but there's nothing like getting your data just right out of the actual Demux run too. And there is an XML file that BCL2FASTQ2 makes that has that information. It's in stats, demultiplexing stats.xml. But of course, it's an XML file. If we looked at it instead of listing this name, the data is all in here, but it's XML, which is horrible. So I give you a little XSLT style template transformation thingy, this file here, which you don't have to care about, it's just a black box. This is a description. Programs that transform XML to other formats are generally have their configurations written in XML because of course. So this is essentially a config file for a program that does XML transformations. And it basically just pulls out the right values and makes a tab separated table out of them. And the command to use that template against the Demux stats, the multiplying stats XML file is XSLT proc. This is the output file that's the plain text summary of that XML file. This is the transformation template, the configuration for XSLT, essentially the program that you want. XLT proc is kind of like an awk for XML, if you like. This is the program that tells XLT proc what to do. This is the XML file that's the input. So, you know, it's sort of like in, out, and program. And then that we can run. I'm in the right place. Oh, we got to use the pre-baked version because we don't have this. We don't have the name on the slide is like as if the live version had succeeded, but we've only got pre-baked. So I have to put the name baked here. And the word baked here, I think. Yeah, there we go. And here's the output of that. And so this is the same data that's in that XML file, but rewritten as a tab separated plain text file. It's a whole lot easier to look at. This most of these columns you don't care about, but the kind of the main part you care about is here's the sample names and some, oh, I guess they're ordered by descending frequency of Demux pile size. I guess that's what's here. So basically here's sample name. And then you got, you know, kind of everything's in tabs here, but sort of like some of these names take multiple tabs so that the columns aren't quite lining up here. But that's column, you know,
That's column 1, 2, 3, 4, 5, and 6 looks like the thing. And what is 6?
6 is 1, 2, 3, 4, 5, 6. Barcode count. That is the size of the Demux pile. This 0 mismatch to 5 mismatch is how many are at various distances. But the first basically the first thing that looks like the real count is the count you're interested in probably. So basically, you know, if you cut this file down to the real essential columns, it's that column and this column, and that's the tally of how many you got out from each pile. Okay. Well, and we're ready to just, you know, we're basically done. We can look at the representation ratios because, you know, I was warning you about like how it was getting bad here. None of the representation ratios are here or anything to worry about at all. So within project 1, looks like my colors are backwards. I guess one's supposed to be red, or I don't know. My colors are backwards between here and here. Anyway, it doesn't matter. I trust the numbers more though, I guess. So I think project 1 is 2.3-fold top to bottom. Project 2 is 1.3-fold top to bottom. Those are nothing to worry about. Within the entire user group, project 1 plus project 2, about 2.6-fold top to bottom, still nothing to worry about. Even if you throw 5x in there, it's still 9x top to bottom, nothing to worry about. So no extreme representation ratios here. We can compute Demux fail because we know the total number of PF1 reads in here. We computed that 1,000 different ways at this point. And we know the size of the Demux fail pile. That's in this file here is default undetermined. This is Demux fail. So Demux fail is 4,816,095 wells. And so we can just take a ratio there, right? So this is Demux fail, and then this is PF1, and that's about 1%. So 1% Demux fail. And if you remember, like from day 1, this is like a typical distribution, and I said like 2% is typically what you get down to 1%. That's really good. Okay, we're done. There's no hidden parts of this lane left to explain or whatever. This lane is explained. Phi-X percentage, size of Phi-X is here. That's 3 million and change, 3.5 million and change. So dividing that by the PF1s, it's about 0.7% Phi-X. Nominal 1% spiking. It's fine. And in terms of utility, and I think in the day 1 charts, here's Phi-X. That puts it here also in kind of like the, you know, it's where the big spike is because that's where we try to target. And then the last thing I used to give is from day 1 is the sort of the overall metric was the fraction of PF1s that go into usable user piles, right? So that's all the samples added up except Demux fail and Phi-X here, and that's 98% of PF1s, and that in the last histogram is like right on the right edge. That's about as good as it gets. So this lane looks great, and we are very confident now that Demux is doing an excellent job in this lane. Doesn't mean that the main reads are okay. Doesn't mean that the science inside the main reads is okay, but anything that's wrong down there cannot be blamed on Demux. We talked about the file naming already. We looked at the reads already. Oh, no, we didn't look at the reads already because that's where I wanted to tell you where the barcodes get inserted into the read names, right? So where are we? Where's the output here? Demux baked. Yeah, okay, so this is the output. So let's look at one of the project 1 guys or something. So let's look at, oh, the first one's fine. Sample 7. 7th entry in the sample sheet. Proj 1, samp 1 in the as a sample name. So let's look at that. So again, it's it's FASTQ 4-line format. We'll just do our usual business here so that we can make that a little more compact. Okay. And what do you see? Remember, this part of the read names used to all be 0 in the pre-Demux stuff. And now what are they? They are the index reads that was used to decide that this read belongs in this pile. Now notice it's not always going to be a perfect copy because we have the one mismatch tolerance. And so actually, I think this is the target. This AGTCAAT, I think, is the target. But look, here's a guy with an N as the first base. Well, that blew it. That's his one mismatch tolerance right there. Right. So he's, but that proves to you that what goes in here is the read and not like the canonical form of what's in the sample sheet. What you actually get in this column is the actual base calls of the index read that caused this guy to go into this pile. So we didn't generate I1 files, but we don't really need to because here's the data that would have been in the I1 file. If you're wondering what happens with dual indices, I think you get the I1 sequence and then a plus sign and then the I2 sequence. All right, maybe we'll take a quick break there. I don't think we're going to quite finish the dual example, which is fine. So day 3 is normally planned to be pretty short, and so spill into day 3 is fine. But our next thing to do is to expand this to the paradigm case, which is interesting because that brings in index hopping, and you can visualize the whole index hopping grid. But let's let me take a 5-minute break and any questions to this one. So you've now actually seen a kind of a whole turn of the wheel, right? You've kind of seen the whole process of the bottom-up approach. Not every permutation of it, handling every conceivable way the runs could be broken, but you've seen the one whole cycle and kind of can imagine how various things could be handled. Oh, after day 3, I'll email them. Is anybody taking this credit? You're taking it. Okay, so then you got it. These are for the part of that's what about that's the whole 98. The whole 98 says that first. No, this one has 2 versions because there's going to be full grid version. Probably these fancy. Sometimes when you copy and paste that, some of those could be non-breaking spaces or something. There's something wrong. There's something wrong. Let's just take away the spot. All right. Oh, because you didn't have you didn't have a front. That goes. Yeah, that goes. Oh yes, that parenthesis matches that. Oh, yeah. That puts that whole thing so that the redirections apply to what's inside.
I know you told me that
I'm part of BSCRC.
right, yeah, but the other four, how they do.
Everybody's doing blind. I mean, right, I don't do my approach for BSCRC lanes anymore either because I can't. I don't have enough time in the day. So that's one of the reasons why the workshop exists, because for those that care to, some science people do is really quite robust, and you can play fast and loose and everything's fine or whatever. But other people are more, conscientious, or they just are investigating a problem that's much more sensitive, or their personality just makes them want to do it kind of in a more careful way or whatever. And then, then maybe you're more interested in this approach. But there's different levels you can attack it, right? Like I said on day one, right? There'll be some things at the end of day 3, just do and don't, just even before you sequence. That'll handle a lot of the problems by just not having them occur. Otherwise, maybe the easiest level to attack is do the index read histograms and look at them, because at least you'll kind of have some hint there of whether things are kind of all looking okay, or whether there could be something going on, even without trying to get into like working around it or whatever. Just getting an eyeball on the top of the histogram will, could catch a lot of it'll catch the worst problems. Yeah, if you want to do the full process though and optimize recovery, get the last bit out or something, or you've got a bunch of your libraries did okay, but then a small fraction didn't, and you're really wondering if that's kind of a Demux problem or is that really a prep problem or something, then you got to dig harder and spend more time. So it all just depends. Some people would say, a rich lab, couple samples fail, they'll just do the whole prep, new biomaterial, new prep, just do it all again, whatever. Yeah. Other people, it may be a sample that is like one mouse that like 3 years to get it to this point or something, or it's like some plant with a weird genotype that grows barely, and some data, some samples are precious, and then what happens, and you got to deal with it because you can't afford to redo it. So yeah, so one of the things that this approach does is that it draws a line around Demux, and you can sort of answer the question is the problem in Demux or not? Because you're trying to do problem isolation, and you're like, is it before, is it after? I mean, if you at least get a point where you can kind of say it's not this, that helps, because you crossed off one of the possibilities. Yeah, always when things go well, but when things go wrong.
A bunch of the stuff we mentioned about custom protocol is considered full.
Well, not only kits, the kind of Demux got pushed to the back of everyone's mind because you just submit a sample sheet, files come back already separated. What else are you going to do? But that doesn't mean that like the problems that used to exist are solved. They're just, you've just stopped paying attention to them. So, yeah. All right, so let's talk about dual indexing. So I think the original motivation for the second index read was because in the older days, we did not have long read lengths on the indices. Like we might have had 6 mers, was the original. TrueSeq started with 6 mers. Like the original Illumina TrueSeq number 1 to 12, they just specify them as 6 mers, and we used to sequence 6 mers. Actually, we were a little unusual because we would sequence 7 mers, because the way the Illumina system works with the pre-phasing and phasing, you should really sequence 1 more base than you really want, because you need to know the base that comes after your base to kind of get the best error correction on that base. And so if that's why, from at least our core, you'll always get like 51 bases instead of 50. Because that means that the 50th base got information from both the 49th base and the 51st base. And so the 51st base actually has a worse kind of overall quality profile than the 50th. So since we said we're going to give you 50, we'll give you the best quality 50 we can give you, and that requires us to go out to 51. That's where the 51 comes from, or the 101 comes. Anyway, but originally there was like six bases, and if you want to, and like, you want at least 3 mismatches apart, say, right? Because, for all the reasons we talked about. And then you can only pack so many indices in at that point. There's a combinatorial optimization problem. It's just it's like sphere packing in a discrete space. There's only so many, there's like certain arrangements that are like the densest you can pack those balls, and that's how many samples you're going to be able to multiplex under those rules. With the indices being this long and the indices required to be pairwise this far apart, there's only so many that you can pack. And what if you want to multiplex more than that? And so that, I think, was the original motivation for I2, because if you had, say, a kit of 12 6-mers, but you could suddenly now put one of them on one end and one of them on the other end, now you can have 12 times 12, 144 combinations. Maybe, I don't really know. I don't really know why we started doing I2. That's my guess, I think, in retrospect. Now we have real reasons to it, which is unique duals and defenses against index hopping. But yeah, maybe I'm not remembering right exactly how they came up originally, but the fact is they exist, and now we can use them to do things. So one way to handle dual Demux, and it's essentially the way BCL2FASTQ2 handles it, is that for most analysis, you simply concatenate the I1 index bases and the I2 index bases, and you just pretend you have a longer index read. That's kind of one way to do it. It's actually not the greatest way to do it because of index hopping, but it is a useful way to think about the process working, in which case you don't really have to explain too much because you already know how single index works, and that just turns dual index into essentially a single index problem. Okay, but the thing is, today each index n can be pretty long, like 18 plus 18 is possible for I1 and I2. And so even a single index can have very high plexity with decent far apart distances, no problem. And that kind of frees up the second index for, we can do other things with it then. We don't need the second index just to get the high plexity. And a great use for second index these days, in which ideally all protocols would do, but protocols are very small, very slow to change, a lot of inertia. But over time, one hopes that sort of all protocols move in the unique dual direction. And so what these unique duals will allow you to do is that this index hopping problem, which you're going to get an illustration of now, what it looks like and how to detect it and so on, the unique duals are basically a way to mitigate it. So you don't know whether it's going to happen or not, maybe, but the unique dual is a defense against it. And it's a very nice defense because it kind of works automatically. You don't even have to do, there's no analysis changes you have to do. You will get the mitigation benefit automatically. If you want to do the detection so that you know kind of what it's, is it really making a difference or not, you have to do a little bit there. But actually, the unique duals give you, the mitigation step is automatic. There's nothing to do, it just happens automatically. And so the way it works is that, so the first situation we were talking about where kind of maybe the reason for I2 to come into existence was to allow higher plexity by, say, getting a kit of 12 and a kit of 12 and then doing all combinations. So if you imagine a matrix with 12 rows and 12 columns, and then you put a library in every combination there, 144. So that is what we would call a dense dual. Okay, so you've actually filled, the design space is this 12 by 12 matrix. You can either put a library in a square or not. And if you actually fill the whole thing up literally, so you got 144 in there, it's a completely dense dual. That's like the worst possible thing you could do. I mean, it may not be any worse than single indexing, really, but you shouldn't do that these days. These days, instead, what you should do is that your first indices and second indices should be paired up in a one-to-one fashion. That doesn't necessarily mean you literally use a particular index sequence for first index and the same literal index sequence here, and it literally has to be the same sequence twice. No, it can be a different set or whatever, but as long as there's just a one-to-one pairing. And so if you expressed it in the matrix, it's maybe still a 12 by 12 matrix. And assuming that you've ordered the rows and columns to respect the one-to-one ordering, what you're now talking about is that there's the main diagonal. And either you can now put a library at every square of the main diagonal or not, but you never put a library off the main diagonal. That's a unique dual. And it's sort of the total opposite direction from the dense dual. And then sometimes people do something in between. Like you can imagine a non-unique dual is literally anything that's not a unique dual. So as soon as you put a single guy off diagonal, you're not a unique dual anymore. But there's a difference between sort of like barely not unique duals, which are kind of mostly diagonal and then maybe a couple guys, versus guys that are like almost completely dense packed. There's like very few squares around. So there's kind of like dense to almost dense. There's like ones in the middle. And there's guys that are almost unique, and then there's literally unique. The best is unique duals, and the reason is because what
index hopping does, and the mechanisms for this vary, we're not going to really get into the mechanisms, but you can, one way it could happen is if there's free adapters floating around somehow. So like during XAMP amplification on the instrument, or maybe during library prep, you had adapters for the wrong index floating around that got a chance to meet a piece of biomaterial that wasn't that index, right? So somehow you got two guys together that shouldn't have gone together. And now even if sequencing goes perfectly, that now looks like a very strong correct tag, but it's from the wrong biomaterial. So, not really, Demux can't really itself do anything about that at that point. From Demux's point of view, everything looks great. But what the unique duals allow you to do is that when that happens, and because the index reads are sort of on the two ends of the molecule separately, is that there's a good chance in a dual that only one of those sides is going to flip. And so if you think of this index hopping process as working in this grid where you've got a guy that's on the main diagonal or something, when one of these index hop happens, the most likely thing to happen is sort of like you either move up or down in the row or over and across in the column. And the nice thing about unique duals is that all of those changes go to squares that you're never going to use a library for. And so you will know that in the sequencing because you will see a pairing of the two index ends that isn't part of your design. So that sort of shows you'll automatically get the mitigation for index hopping because you won't have a target for those, or whatever target you do have for the off diagonal pairs are simply to have them go someplace that isn't in the wrong pile, right? I mean, they can either drop out of the analysis or they go to a specific bucket that just collects them. So they don't go into the place where they're supposed to go. I mean, it takes like a double error to get them to go to a wrong place, right? So you'd have to kind of corrupt both the I1 and I2 and get them consistently corrupted to kind of land in another guy that then looks like something. I mean, it can happen, but it should be it should be an order, it should be a different order kind of probability event than a single corruption. Compare that to a dense dual. Now, any corruption of I1 or I2 lands you in another library that you use. Now you can't tell. Or suppose you do single indexing. It's still happening. But every flip, it's like kind of the totally dense case, right? I mean, with single indexing, every time you flip from one of your indices to another one of your indices, well, of course, that looks like the other library. There's no chance it's not even a chance to be able to be something that's different, right? So it presumably happens all the time. We think it's ubiquitous at maybe the level of 0.1% or something, 1 in 1,000. But it not infrequently can hit the 1% level, and then when it's bad, it goes over it. So in single indexing and in dense duals, you have no defense against it, and you have no ability to detect it. It's just silent. As your dual empties out, so as the density of your dual goes down, and you have more holes in the design, you have more chances that the corruptions land in a guy that you can see. And now you can see the misty muck. You can see the index hopping happening, and those no longer cause misty mucks at that point. And so unique duals is the idea that you should maximize that ability. The way you maximize that ability is using just filling up the main diagonal, leaving the entire rest of the matrix empty, so that you kind of maximize the chance that when something gets corrupted, it lands in an empty square. That's the whole idea. So, all right, so I kind of flipped it around. That's really kind of where we would end up with this example, but I kind of I front loaded it now. So we actually need to run the example so we can get the data so we can show the grids and stuff like that. But that's kind of where we're headed. Probably at the start of day 3, depending on, we got 15-minute service. But day 3 is near the beginning of day 3. You'll start to see kind of these hopping grids and stuff and whatever. So the example for duals we'll use is kind of the sister of the lane you just saw. It's ZBP 099 instead of 098 lane 1. And this is, again, a paired in 5151 main reads. It's now a dual index. So there's 8 NT first index, 8 nucleotide second index, which is the same as the lane physics you ran. And the user expects a 12-plex non-unique dual. They have, I1 is actually distinct and is already enough to identify the 12 samples. I2 only has 6 distinct sequences. Each of the 6 sequences is associated to exactly 2 distinct libraries. All right, so basically
there's only sort of half as many I2s as there should be, and each one of them is doing double duty. Just shared by 2 libraries. The non-Demux run for BCL2FASTQ2, almost exactly the same command line. The only thing that's going to really change is the use bases mask. And so now, again, for this example, I deleted the data, but I didn't even get permission from the user to share this one, so I can't share the run folder even, so it doesn't really matter. But kind of, you saw this Y1N50 in the other example, that's nothing new. But now there's 2 indices, and so now we have to say I8, I8 in the use basis mask, saying that we're going to have this first I8 says your I1 reads will come from the first 8 bases of the first index, and your I2 file reads will come from the 8 bases of the second index. But other than that, it's the same. But now we need to make 3 histograms instead of 1. We will do the I1s independently, the I2s independently, and we will concatenate the I1s and I2s and do another histogram of those. And the command lines to do that are, we already talked about when we did the first histogram, what the command lines for that looks like. And then I've got them pre-baked here, and this is what they look like. The single I1 and I2 look just the same as the histograms you've already seen, because it is just literally another histogram of exactly the same type. So there's the I1 one, there's the I2 one, but then how does the pair one look like? It looks like this. Okay, so now you've got first column is the I1, second column is the I2, and there are, like, this first one, the top one is almost 69 million of this particular pairing shows up. And what do you see again? You see the same kind of, you're now going to analyze these in a very similar way that we did the previous example. You can already look at this and see, okay, those look like real pairs. These are starting to look like other things, maybe this guy in the middle, that's actually going to be phi x again. That's actually the I2 for phi x. So you can already kind of see that the pairs, kind of what those are going to be like. You're going to use the Demux helper web tool, do the little game with the stars in green and white, and looking at the stuff and making decisions. Here we're looking at the I1s, and that's pretty easy. Those are going to be real probably. That's phi x. And then these look like, they're what, 200-fold down from this guy. That's probably the base call errors of these. And some of these you can probably even directly see, right? So actually, like, that guy is going to be a corruption of that guy, right? Let's directly see it. Here's the I2s. Now here we're only expecting 2 distinct I2s, I guess. And we're seeing a little, oh no, so I said 6. I said 6, right? So 1, 2, 3, 4, 5, 6. There's I2 for phi x. And here's poly G showing up in I2, which is not phi x's I2, but like I said, poly G dark tends to show up. So does poly A. That's not that much of a surprise. Anyway, those are probably empirically the targets that we would keep for I2. Anyway, so it just goes like that. So you have to repeat the kind of things that we did there, but the first step to analyze a paired lane is to do the I1 and I2 separately, very much in the way that you do a non-dual lane. I will name, it looks like empirically you get 12 distinct I1s out of this, which I'll call A through M in order of frequency. And then for I2, you get, well, there's going to be 12 user ones, and then there's the phi x one for the I1. For I2, there's the 6 user ones, then there's the phi x one, and then there's the extra poly G one if you want to throw that one as well. So that makes, what, 8 or something. I'll call those 1 to 8. So this way I can refer to pairs of them like C7 and D4 and whatever, and you know what that means. So the letter is the I1 and the number is the I2. And what about these transitions where you transition over? Actually, this is actually quite an interesting example because it shows you some of the systematic indel corruptions of things. In fact, the very next guy in the I1 histogram, this red sequence here, is a 1 indel to D. So here is D. Actually, I think I've got the little alignment over here. So I don't remember what the top or bottom is. D, A, C, T, G, A, G, C, G. So the top row is the expected one. The bottom row is this one, and they are an indel apart. Right? So the G here got deleted. And then of course, because the indices are always sequenced to the same length, deleting this G exposes some new base on the end there. So, this base, we don't really care in terms of declaring this an indel. It's the fact that this G got deleted. So there you go. In fact, the first thing that's not an exact match to kind of the expected list ends up being a systematic indel. So there you go. There's another example. The next one is a one mismatch, no indel, it's just a straight up one mismatch to B. Anyway, so there you go. How about the I2s? Well, as soon as you get out of poly G here, which was kind of that extra guy, this one being phi X there, where are you at? Single mismatches to all these guys and stuff. So that's the bottom of that one. And here's the number of PF1 wells in the lane, same kind of command we ran before that can use the histograms. And rather than having one file that we send into R for the list of guys that we kept as targets, we now have two files. We need the I1 file and the I2 file. And then so at this point, we've decided what I1s are present and what I2s are present. Now the question is what pairs are present. But because we've sort of already decided that I1 is like this and I2 is like this, now the space is sort of more limited. It's all the combinations of these I1s and these I2s and not like pairs of any kind whatsoever. I mean, we will look at the histogram of pairs. And if we saw a high frequency pair that actually wasn't one of the I1s we had and I2s we had already identified, that would be kind of weird. And then we would reevaluate maybe what our I1 and I2 list is. That doesn't happen here. So actually the top of the pair histogram is all combinations here, like A1, B3, C2, B4, and so on. And then actually we get, well, actually then the next one here, which I've shown in gray, just because the coverage has really dropped off at this point, is still an M4. These are still pairs that we have. Of course, at this point, though, we're kind of more pairs than the user said they were supposed to be, right? What did I say? There's 12 or something. The user expected 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, phi X. We think and then the representation drops off. But oh, look at this. It's an M4 and then an M3 and an M2 and an M1 and a B8 and so on. So there's still pairs of things we got. But those are no longer, those were not expected to be filled from the design. And some of these involve low mismatches, right? So like this one is 0 mismatch in I1 to I, but it's 1 mismatch in I2 to number 5, but it's still clearly an I5 guy, and so on. Anyway, so if we make a little grid here and say empirically, the pairs that we kind of really look present is kind of this stuff here. And that's, you know, it doesn't look like the main diagonal because you'd have to permute either the rows or the columns here, but you could make this be on the main diagonal. It's just the fact that I don't quite have them in the right order. It's because I've strictly ordered these by like 0 mismatch descending frequency, and that just doesn't happen. It does pair up 1A, right? But sort of like 2 and 3 should be swapped or something so that like it's B2 and not B3. Anyway, you can imagine permuting this so it is just diagonal. Well, this isn't a unique tool, so it's not a diagonal. But if you look, the user design is supposed to have what? Each row should be unique, but each column should have exactly 2. So the I2s were shared 2 each, right? And that's kind of, this kind of looks right? Like, so it's like unique. Rows are all unique. 2, 2, 2, 2, 2, 2. That's looking good. That looks right given the user's expectation. We do have phi X down here, but then we're starting to get these gray guys, which are actually other squares, and that's going to be index hops in this guy. And actually in this lane, the index hops are around the 1% level, so it's the higher end of normal. You can actually use the empirical Demux helper web tool even in the dual case. You simply remove the tab between the I1 and I2 and just pretend that the longer sequence is a single index, and you can kind of work with it that way. Okay, so then maybe we'll do a little bit of this more tomorrow, but I just kind of want to show you one of the grid pictures today. But we're basically going to do in R the exact same thing we did before, but all the analyses have to be repeated twice now, basically. We have to do like the I1 version, the I2 version, and so on, and just kind of repeat everything. So I've now taken some of the code that we just had run once before and packaged up in little functions so you can like call it twice or 3 times or whatever's needed. But we're basically going to construct the same histograms and stuff all as they were before. We're going to make decisions on what Demux tolerances to use. I think it ends up just being 1 mismatch in I1, 1 mismatch in I2. And then when we go to do our big analysis and so on, we have to keep track of a little more data because now we have to track of pairs instead of singles. So we just have some extra columns that we didn't have. But in the end, we're going to end up with a matrix again, which is very similar to the matrix we had before. Now, if you'd like, you could do a 3D matrix where it's now I1, I2, and the third dimension is mismatches. But it's more complicated than you really need to go. And since we've already kind of decided that I1, one mismatch tolerance is good, I2, one mismatch tolerance is good, we can just collapse that third dimension by allowing just less than or equal to 1 mismatches and go to a just straight up 2D matrix where now it's just straight up I1 and I2. This number in the square is the number of reads that Demux under 1 mismatch tolerances to that place. And we're not going to worry about the guys that are higher mismatch because we've already kind of looked at I1, I2 independently, and we're not worried about that. We explain almost all reads that way, and so we're not worried we're losing stuff with higher mismatches. And this then is something we can now plot, right? So that if you visualize that with colors, say, or something on a log scale, you'll get this. So here is the log color scale. So this is, I think, log base 10. So, this is like 1 million reads, 10 million reads. This is 100 reads. So this scale is going from like 10 reads to almost 100 million reads in this color scale. So, of course, what you see are these hot red guys. And what do those correspond to? Well, it's exactly the ones we kind of identified as what we think is present. But then there's sort of this whole background of yellow and even orange. And where is that on the scale? Well, that's somewhere between 5 and 6, whereas the reds are somewhere like 7.5. Well, 5.5 and 7.5 are only 2 apart. Well, 2 apart in a log 10 scale is 100-fold. That's the 1% index hopping in this case. So what we're seeing is actually every single combination of our 2 indices is showing up, and not like a little bit, like 1% of the overall average. It's like you can't explain that by like machines making up sequences or whatever. I mean, if it was random, you'd get sequences that didn't even match I1s and I2s, right? This is something else. And so this is the process happening here. And the fact that this is a low density dual, it's not a unique dual because of the 2, 2, 2, 2, 2. But we have a lot of empty squares, and that's allowing us to see the index hopping. If you recluster this, repermute the rows and columns, which is often a great thing to do for these kinds of index hop matrices, you'll see these groups, the 2 guys that share each I2 together, like this. And we have some more to talk about, but just sort of like just to kind of leave you with a kind of a nice picture. Here's a collection of sort of these matrices that we've seen over the years. And you can kind of see all kinds of things happening. So like some of these have block structure, even nested block structure. Like here you see these big blocks and then these diagonal lines. That's completely related in this case to the grouping in which the samples were prepared at the same time on the web bench. Then you get cases like this, where it's sort of like everything hopping to everything. That's much more uniform. That's more likely to be related to something that happened on the instrument. And you get all kinds of things in between and so on. Anyway, so we'll talk more in depth tomorrow, but we're out of time today. So I'll stop the recording there.